Okay, today we're going to cover another exciting topic as promised, interconnects, and this comes well after we cover multiprocessors, because if you want to, and cache coherence and consistency, because if you want to build anything scalable, in the end you're limited by the interconnect with which you're interconnecting things with. I think this is very fundamental. So designing much more efficient, much faster interconnects is still a big challenge, basically. What kind of substrate do you use? How do you connect things? What kind of algorithms you use? So we try to cover a lot in a lecture, maybe in a lecture and a two, but there's a lot more on this topic than what maybe meets the eye in a lecture, basically. So we're not going to cover, for example, medium for interconnects like optical interconnects. We're going to assume electrical interconnects over here. Although a lot of what we're going to cover is really going to be fundamental to pretty much any interconnect you design, except we're not going to look into the technology implications, underlying technology implications as much in these lectures. It's going to be more algorithmic and design implications at the high level. Okay? Does that sound good? Okay. So basically last time we covered these things, so hopefully it's fun. We will release the last lab also at some point. You don't have to do it, but you can take a look at it if you're interested. It's an optional lab. People have fun with it. Basically that's the lab where you implement a MESI cache coherence protocol, which is essentially the basis of cache coherence protocols that are used in existing computing systems, most existing processors, if you have cache coherence, and most of them they have cache coherence. And when we talked about cache coherence, we said that it's important to make it scalable, especially if you want to build 10,000 or 100,000 node processors. And we discussed the scalability issues with two different mechanisms for cache coherence. One was Snoopy coherence, and the other was directory-based cache coherence. And we discussed that directory-based cache coherence is scalable, right? And one of the things that I mentioned in one of the slides was it's as scalable as the interconnect, essentially, in the end, because it relies on messages. Essentially, scalable directory-based cache coherence is really a message passing system where you send a message to the directory and the directory sends responses to you. You basically communicate via messages, right? And in that system, basically, your scalability is really determined by the interconnect itself. So that's why we're going to cover interconnects, essentially. But interconnects are broader than that, of course, and these are some readings. This is not a comprehensive list. We're going to talk maybe about this, not tomorrow. Tomorrow we'll have a review session, but we'll figure out when we talk about that. But you're not going to be responsible for what's covered next week, essentially. So next week you'll probably have a free lecture or time to study for your exam. But we're going to cover some recent work on making interconnects energy efficient. So when interconnects first started, performance was a big concern, but energy efficiency became a much bigger concern recently. And there are a bunch of recommended readings. You can see that some of them go as early as 1979. This is a favorite paper that introduced the concept of multistage interconnection networks. So people actually are tackling interconnection network problems for actually almost as long as the computers have been built. In fact, I'm actually going to, I should have recommended another paper over here by Paul Baran. It's called On Distributed Communication Systems. It was published in 1962 as a technical report, and that talks about a lot of the networks that are considered to build distributed systems, and foreshadows some of the communication protocols that are on the internet, actually. Okay, I don't know why we have this problem, but this is an interconnect problem too, probably. So interconnects go all the way down to very basics, clearly. So let's talk about some basics first of all. If you want to talk about basics, then the first question is, why do we need an interconnect? Essentially, we want an interconnect to connect components. And components can be really anything, basically. In the end, if you want to connect X to Y, you need some sort of interconnect. So this is an interconnect, actually. I'm walking on an interconnect, right? It's a medium, you can consider it that way. Roads are interconnects, right? They connect whatever they're connected to, essentially. They connect nodes to each other. And nodes happen to be cities, villages, or whatever thing is attached to the road. It's similar over here also, right? You have an interconnection network in a computing system, and it can connect processors and memories, processors and caches. Clearly, it can connect stuff inside the memories also, like banks, subarrays. caches and caches, and I/O devices. So basically interconnects are everywhere, and you can imagine that there are many, many forms and shapes. And we have seen in the memory lectures a lot of interconnect actually, even though we didn't go into a lot of the detailed treatment of interconnects, it was always there, right? We said that because of the long latency of interconnects, memory latency is long, sub-area latency is dominated essentially by the local bit line that you have and the sensing that you need to do on that interconnect. And if you want to reduce latency, you want to shorten that interconnect, right? Clearly, it's very fundamental. And we looked at different methods of shortening that interconnect. We looked at different methods of partitioning or connecting different interconnects with each other so that you can actually move the data much better. If you remember the low-cost interlinked subarrays paper that essentially looks at how to interconnect different subarrays using isolation transistors at the boundaries, right? So it's really all about the interconnect when you think about the majority of the memory latency, at least in DRAM. And that's true in a system like this also. I mean, it could be true in a system like this also. When you're communicating between this node and this node, you may be bound by the latency that you have on the interconnect. And whatever you do in this interconnect is going to affect your performance significantly, clearly. Okay, so why is it important? I think I've already given you some of the important reasons, right? Clearly, it affects the scalability of the system, how scalable of a system you can build. If you actually have a non-scalable interconnect over here, which we will see like a bus, then you may not be able to attach thousands and thousands of nodes to it, right? The existing internet clearly doesn't operate using a bus. It's a very heterogeneous interconnect that we have, and it's many, many different types of cables and wireless communication media that we have in the internet, right? Okay, so and the cost of the system, scalability is also very much related to the cost. That's why I like putting both of them over here, because how you build that interconnect clearly has an implication on cost. So it also affects how large of a system can you build, and also how easily can you add more processors, right? If you don't have a flexible interconnection scheme, then you may not be able to add more processors, both at the physical level as well as the algorithmic protocol level. You need to have mechanisms to be able to add processors or whatever nodes that are going to communicate with each other, such that the physical medium supports it. So you load, for example, add another processor on a bus, the physical medium might break, right? Because you loaded the bus too much, and then you're not going to get good signal integrity over there. So that's one example of a physical medium not supporting an additional processor. But also your protocols need to be able to support it. Your protocols need to be flexible enough that you add something and automatically everybody can communicate with it somehow after discovering it, for example. The internet is very good at that, for example, today. Okay. Clearly it affects performance and energy efficiency, and we'll talk a lot about that today. Actually, we'll cover a lot of these in today's lecture. So how fast can processors, caches, and memory communicate within the context of a processing system? How long are the latencies to memory? How much energy is spent on communication? And in the end, if you remember when we talked about memory, the energy that's spent on a DRAM access was mostly due to the interconnects that you have between DRAM and processor. And if you eliminate that, the majority will be due to the interconnects inside the memory chip, right? Essentially, in the end, you go back to the interconnect. Now, this is very much dependent on the technology. Of course, DRAM is different from phase change memory. In phase change memory, you have some other way of accessing. So interconnect is still important, but the cell access time, in terms of, for example, the amount of energy you spend for heating up the cell, is something else. It's a bit different over there. Whereas in DRAM, you're mostly dominated by interconnect. That's true for SRAM also, in charge-based memories. In resistive memories, your energy consumption actually shifts a little bit to how you actually really access the cell itself. And that requires some additional heating, for example, that's not really interconnect-based. Okay. On top of this, of course, it affects your reliability and security. I'm not going to talk a lot about these over here, but I'll give you some examples. For example, can you guarantee your messages are delivered or your protocol works right? If your underlying interconnect doesn't provide any guarantees, clearly you have some reliability requirements at the high level. How do you satisfy those reliability and potentially security requirements, right? And I say security over here, right? Security is clearly very broad, even broader than reliability potentially in this context. But whenever you go off the interconnect, you're visible to someone else potentially, right? And a lot of the potential attacks could be done because of that visibility. Anyway, we're not going to talk about those aspects of interconnects in this lecture. Any questions so far? Hopefully these are basics, right? I asked you before, but how many of you have taken a networking course? Networks. Okay, so these are probably familiar concepts. Maybe a different treatment. Okay, so I'm going to give you a bunch of terminology to begin with. Hopefully it's not going to be boring. Some of it is boring, I think, but we'll go over the boring parts relatively quickly. These are some things that you need to know. I think these are the fundamental parts. These are not the boring parts, I think. Basically, any interconnect has three types of characteristics, let's say. You have a topology. You need to route over the interconnect, and you need algorithms for it, and you need to decide on buffering and flow control, how you handle those. Basically, whenever you're building a computing systems, if you're the architect, overall system architect, then you need to decide on all of these. So what is topology? Basically, topology specifies the way switches are wired, the way nodes are connected to each other. So it affects everything else, basically. It affects your routing, it affects your potentially your buffering and flow control. Not exactly, but it may limit the choices that you have in terms of this, for example. It affects clearly your reliability, throughput, latency, and how easily you can build this. And we will cover a lot of different topologies, not everything, of course, because many topologies have been proposed over decades and decades. But we'll cover some of them since it's so important. And going forward, it's still important, I think. But what is more important, I think, is going forward, how do you design a lot of these things at the same time such that you get a more specialized system for different applications? That's something that has not been covered as much in the past. You'll see that there's a lot of work, but a lot of work is in the general purpose domain. Whereas today, as you know very well, we're in the more specialized domain, clearly, right? We have these applications that we really care about. And if you want to make them maximally efficient and fast, we really want to somehow specialize the architectures and the system we designed for it. And Interconnect is really a big component of that system, actually. So I think some of the accelerators that I see that are being built are using really general purpose mechanisms for interconnection. And it's not clear to me that it's a good idea if you really want to get the highest performance and efficiency you want from that system. Clearly, general purpose communication mechanisms are good for programmability, right? There's also a tension here. If you go more special purpose, maybe your programmability reduces, but if you want to really specialize, maybe you want to take that trade-off. Okay, so topology is very important. We're going to cover a lot of it. On top of this, routing is important. Topology affects routing because topology affects how your nodes are connected to each other, which fundamentally means that it affects how you can route a message from one node to another, right? Clearly, if your topology is like a bus, you don't have a lot of choices in your routing. But if your topology is more like a graph, like a random graph that is not regular, that's irregular, then you have a lot of choices in your routing, clearly. Of course, you need to know how these things are connected, because you may have, if you go one path, you may not be able to reach some destination that you're trying to reach, right? Okay, so routing essentially says how does a message get from its source to the destination, clearly. So there could be many examples of it, and we're going to cover it after we finish topology. It could be static, it could be adaptive, and the most aggressive forms of it are actually completely adaptive, basically. You don't have any static information. But you could potentially do this statically also. If you know your source, if you know your destination, you could actually specify the route your message will take before you send that message. Your compiler can potentially do that, and that will be embedded into your packet, and your packet essentially follows that. And we will see that there's a benefit to this. If you actually have this information, if you do this, your routers become very simple. Right? Your routers don't need to figure out, oh, I got this message and the destination is there, where should I send it? They don't need to do anything because it's already encoded in the message that you're supposed to send it this way. Right? So clearly we have very similar trade-offs like in the software-hardware interface, static versus dynamic decisions. If you already have the static information, you can make the hardware very simple. If you don't have that static information, your routers need to become much more complex now. Okay, so buffering and flow control is the last one over here, but not the least one. Basically, this you answer the question of what do you store within the network? Entire packets, or within a network router, let's say, entire packets, parts of packets, or some other things. How do you throttle during oversubscription? And how do you build the router? Does the router actually store the packet, or does it actually do something else? Right? We will see different options over here, because you don't really need to store packets in a router also, right? Because you can drop packets if you're oversubscribed. You can actually deflect packets, as we will see also. Okay, so this is very tightly coupled with the routing strategy, clearly, because if your routing strategy doesn't accommodate you to drop packets, then you should not drop packets. Right? It's not just the routing strategy, but it's also the topology, actually. In some topologies, you cannot deflect, for example, meaning send the message to a destination that it's not supposed to go to, because you don't have enough ports in the system. And if you don't have that, you cannot do some of the routing and buffering and flow control decisions that we're going to look at. So these are all coupled with each other in the end. And the best system, as you know by now, is built by understanding all of those and how they interact with each other. Okay, so let me give you some more terminology. So hopefully these are clear. These are the more fundamental. We're going to see this over and over. And whenever you build any interconnection network, you'll have to ask these questions basically. How do you do the topology? What is the topology? How do you do the routing? How do you do the buffering and flow control? Flow control is essentially how do the packets flow and how do you control the movement of packets from one node to another node when they actually go from their source to destination. You need to control that flow essentially. Buffering is hopefully obvious. Okay, some more terminology relatively quickly. We're going to use some of these things. That's why I want to define this terminology. Clearly, there's a network interface, and this is essentially a module that connects an endpoint to the network, like a processor. Essentially, network interfaces are used to decouple computation and communication. If you look at the textbook definition of it. So it's good to have that boundary sometimes, but sometimes it's good to break that boundary also, because as you know, sometimes computation and communication need to be done at the same time, right? Link is a bundle of wires that carry a signal. Hopefully this is obvious. Switch or router essentially connects a fixed number of input channels to a fixed number of output channels so that you can actually switch between them. You can go from this input channel to this output channel. That way you can actually change where you're going in the network, in a graph, for example, right? We'll see many switches. And channel is a single logical connection between routers and switches. This may be different from a physical connection, as you will see. Okay. If this hasn't confused you, don't worry. Or if this has confused you, don't worry also. Clearly, there are also more terminology like node. A node is a router or switch within a network, so it's very general. But it could really be anything that's, I think of this as anything that can be connected to the network, and that clearly requires a router or switch in the end. Because if you have to connect to the network somehow. Maybe more general thing should be the arbiter, right? Because a router or switch is a bigger form of an arbiter in the end. A message is a unit of transfer for network clients. So for processor memory perspective, you send a message. This doesn't mean that network actually delivers the entire thing as a chunk. It breaks that message into what's called packets. That's the unit of transfer for the network itself. And the network, at some level, understands a packet. And underneath, of course, you can think of this packet as a logical size of a unit of transfer for the network. But there's also a physical size. Underneath, your physical connections may not support that big logical size. And the network itself, the network interface, for example, or the router, may divide things into smaller pieces. And those smaller pieces are called flits. For better or worse, it's called flow control digits. This is the granularity at which you do your flow control, actually. Basically, if for example, if your physical link is 64 bits, your flit may be 64 bits. And if you want to send a packet for, let's say, 64 bytes, a cache block, then your packet consists of 8 flits, right? That's the idea. And then you need to send the packet in consecutive 8 cycles over the physical link. So hopefully these are obvious. This is not any magic. This is just terminology. But you will see this terminology in papers used. That's why I would like to put it over here. And it's very common terminology in especially interconnection networks that are built for processors today. Actually, supercomputers also. Supercomputers is another story. If we get to it, I will talk about this interconnection network clearly affects the performance of the biggest supercomputers, and the wiring complexity in supercomputers is a big problem. That's why going into a medium like optical links is very nice, because it gets rid of a lot of these electrical wires that are really difficult to route by a human. Because if you're building a big supercomputer, you need to route these huge wires, and you have to ensure that they're connected between the correct nodes. And if you're not able to do that, then you may actually get incorrect communication, right? Okay. Some more terminology. Basically, there's direct and indirect networks. This is best understood with an example, probably. Basically, here, the endpoints sit inside the network or outside the network. Inside means direct, outside means indirect. So this is an example of indirect. Basically, these are endpoints. You can think of this, let's say, processors and some other processors, or processors and memory banks. And this is an indirect network over here, because the endpoints are outside network, and these are only switches. Basically, these are just routers. We will see that this is an example. This is actually a butterfly, but this is an example of a multi-stage logarithmic network. It's really a multi-stage network over here. Yeah, basically this is a router over here. It has 2 inputs, 2 outputs. More terminology for you. Radix is really how many inputs do you have and how many outputs do you have. And this is some more terminology that you may see as you read papers, basically. Basically, these routers are 2-array, whatever that means. That's the radix array network. Somebody defined this terminology, and I'm not responsible for it, sorry. But you will see this like n-array, right? N-array is n-input routers, essentially. Okay, it's beautiful, right? It's butterfly over here. Okay, this is a butterfly network. It's used in some systems. And this is another network. This is a mesh network over here. And this is direct in this case because every node, as you can see, at least this is a direct mesh. Not all meshes are direct meshes, but this is an example of a mesh that is direct because every single, basically the endpoints or the nodes that communicate with each other actually sit inside the network, as you can see, right? So every router also has an endpoint over here. Okay, I think that we're done with this terminology, although I'm going to introduce some more later. But let's go into the topology itself. So topology comes with its own terminology also. Topology can be regular. Essentially, topology is how the switches are wired. So this is actually, I've shown you 2 topologies over here. This is a mesh, 2-dimensional mesh, and you can see that there's a particular way of wiring these. Each switch is connected to its neighbor, except when the switch is on the boundary, right? When the switch is on the boundary, you don't have some of your neighbors present. Basically, you don't have 4 neighbors. You have only 2-dimensional neighbors, let's say, on this side. So, of course, this leads to some implications. If you actually place this over here and place this over here, there's no way they can communicate with each other nicely, right? They have to go through the entire network. Whereas if you, even though they could be considered neighbors, if you actually had a 3-dimensional link over here, right? Okay, and this is another topology over here, and you can see that in this topology it's a multi-stage network, and you have only switches. And if you want to communicate between this node and this node, you have to go through the appropriate switches, right? Whereas here you have more freedom in a sense, right? Depending on your routing algorithm, you can actually, if you want to communicate between here and here, you don't need to go this path, for example. You can go this path, or you can go some random path over here, right? And you can actually go a little bit and then go back and come back, right? So the routing algorithm is clearly more flexible in this case. Yes?
In this mesh, is the endpoint and processor, are they physically the same, or are they just connected like that? Is every processor actually a router and the processor, are they physically the same thing, or?
They don't have to be physically the same. Yeah, they're just connected like that. Basically, you can have a router, and then the router can have communication with the processor. Okay, we'll see more examples. Any other questions? Okay, so let's give some more topology. Unfortunately, some more terminology, but this is useful, hopefully. So clearly, regular, irregular. If the topology is a regular graph, mesh is very regular, as we've seen. Ring is going to be regular, but you could also have completely irregular graph, right? That's obvious. And I believe internet is very irregular. There's no dictated topology on the internet, for example. Routing distance is number of links or hops along a route. Hop is essentially one link you traverse is considered a hop, essentially. Right? How many links do you need to go from a source to the destination as your routing distance? And route is essentially a route between a source and a destination. So diameter of the network is the maximum routing distance within the network. This is used to understand the maximum latency within a network. So if you have a large diameter, then you have a large routing distance, which means that the maximum latency that you get in a network is probably very high. But of course that's not enough, because routing distance doesn't take into account the actual latency itself, right? It says how many links, But it doesn't say how many nanoseconds, for example. In the end, what you care is really about nanoseconds. But low diameter in general is desirable if you want to minimize the latency, because it minimizes the number of hops you go through for any message. And the more hops you go through, the likelihood of switching overhead increases, clearly, because you go through some router, right? Average distance is the average number of hops across all valid routes. And usually you can calculate this without any workload present, right? Clearly you can look at the network and you can calculate this, right? You need to know the routing algorithm potentially, right, to be able to make that decision. But of course, workload-driven metrics are much more interesting. But people have used these metrics in the past to understand networks. Because they were, one of the reasons was actually because they weren't able to simulate very large-scale networks in reasonable amounts of time. So they developed some of these metrics that were quick and easy to understand metrics that basically characterized a particular network design. Okay, another metric that is like that is bisection bandwidth. You may see this basically. I'm not going to go over this in detail because I don't like this metric that much, but you will see this in papers. It's often used to describe network performance, but basically what you do is you cut the network in half and sum the bandwidth of the links that you cut, essentially. So, or you can think of this as minimum number of channels spanning the two halves of the network times the bandwidth of each channel. And this is of course meaningful if the topology is recursive and regular somewhat. But basically this essentially gives you an idea of what is the communication bandwidth that you have between two halves of the network, which hopefully is an indicator of the performance. But clearly this doesn't account for many things like switch and routing efficiency, and certainly not execution time. But you will see this in papers. There's also another distinction, which is very quickly blocking versus non-blocking. You may actually see this. This refers to the flexibility of the network. Basically, if connecting any permutation of sources and destinations is possible, the network is non-blocking and it's very flexible. Otherwise, it's blocking. And there's something else called rearrangeable non-blocking. So you can make some non-blocking network by rearranging the connections when switching from one permutation to another. So it's kind of somewhat dynamic reconfigurability actually. But I'm not going to talk about this, so don't worry about this if you're not interested in this. But you will see this in the terminology of literature. And there is a lot of literature. Any questions on the boring terminology or the interesting ones? Okay, so now we're done. Now we're going to look at more, but we're going to use some of this terminology in understanding this. We're going to look at some topologies. I'm not going to cover every topology that's been proposed in life. There's a lot. And people are proposing more and more these days. Especially low diameter topologies are very interesting today because you want to minimize latency bounds. And also low diameter is also good for energy, I think, because you don't need to switch as often. For example, internet I think consumes a lot of energy and wastes a lot of energy because you switch a lot going from one destination to another. Wouldn't it be nice if actually diameter was like the diameter between any computer was, let's say, 2, which means that going from one computer to another computer you only go through one additional switch. That's not going to happen, right? That's not easy. But you could do that when you're designing an on-chip network, clearly, right? Because all of the design is in your hands. In a network, in an interconnection network like the internet, it's very difficult to do, clearly. Okay, so now we're going to start with the simplest topology, and we're going to make it more complicated, and we're going to switch between simple and complicated a little bit to see the benefits of a topology. And there are clearly many metrics to evaluate an interconnect topology. We're going to look at some of them. Cost is important, latency is important, contention is important, how much contention you get when you have a lot of communication. Scalability is important, and we're going to cover that even though it's not written over here. And there are many others that exist that you should think about. I think energy is an important one, even though I'm not going to explicitly cover it in the topologies. Bandwidth and overall system performance. Of course, once you go to higher level, application level metrics like energy and system performance, then your communication patterns start mattering a lot, right? Because that determines how you exercise your underlying network. But some of the other things like average latency or average distance as we defined it, or maximum distance is independent of your communication patterns. Of course, you can define them as dependent on communication patterns. Okay, so this is the simplest topology. You've seen this before. This is a bus. It has 8 nodes attached to it, or 8 endpoints attached to it. Essentially, it's a topology where all nodes are connected to a single link, and they communicate over that single link. And whenever a node wants to send a message to another node, it basically puts an arbitration request, and there's some sort of arbiter that arbitrates across all of those nodes, clearly. And there are many arbitration mechanisms proposed. It could be more centralized arbitration, it could be distributed arbitration, which requires very interesting sensing methods on the circuit itself. In the end, that arbitration is the bottleneck for scalability for this bus. Well, that's one of the bottlenecks, actually. But basically, this is another bus. As you can see, this is a more concrete example. You can see processors and caches, and they're connected to the memory over here. And you can see that this is actually used as a Snoopy bus. Basically, these are caches that can easily implement a Snoopy coherence protocol, right? That's essentially what we showed in the coherence protocol lectures last time. Okay, clearly this has some advantages. It's simple. It's conceptually simple, and implementation is simple also, right? You just lay out a single link over here. And for a small number of nodes, it's cost effective actually, because you don't want to do something more sophisticated. And it's easy to implement coherence over here. You can do snooping and serialization. And you could actually do tricks over here. You can pipeline the bus. You could actually do a lot of the tricks that we've discussed in microarchitecture to take advantage of it. Of course, once you go to pipelining, you may need to be more careful about how you actually do the coherence, right? Snoopy bus. But I'm not going to go into the details of the bus design. That could be an interesting lecture, clearly, but maybe not as interesting as a broad overview of interconnects at this point. Okay, but what about the downsides? Clearly, there are multiple downsides. Basically, it's not scalable to a large number of nodes because it has limited bandwidth, essentially. As you keep adding nodes, what happens actually is multiple things happen. One is you get higher contention because more nodes are communicating with each other, right? And as a result, this bus becomes a bottleneck quickly. Okay, maybe it can sustain one transfer between, at any given point of time, it sustains only one transfer between two nodes, right? Two node pairs. But if you have 10,000s of nodes over here, tens of thousands of nodes, they need to communicate with each other, and they cannot do that concurrently. Right? Clearly, you can partition the bus, you can play a lot of tricks, you can pipeline the bus. Now it starts becoming less simple if you start partitioning and pipelining and adding hierarchy to it. Maybe you can have more hierarchical buses, which I'm not going to go into. That enables more scalability, but that makes it more complex also. So if you think about the simple abstraction, a single link, 10,000 nodes, that doesn't work. You need to do something else to scale it. It doesn't work for two reasons. One is you get high contention, and you get unnecessarily high contention in a sense, because let's assume that you have nodes 0 and 1, and they're the only ones who want to communicate with each other. And you have nodes 6 and 7, they're the only ones who want to communicate with each other over here. Does it really make sense to have a single link to be disturbed by every single communication that's happening in the system, right? So that disallows, because you have a single link, that disallows communication by any other node pair at the same time. Okay, so that's one of the reasons why it's not scalable. But there's another reason why it's not scalable. As you add more nodes on a single electrical link, you get significantly higher additional higher loading on the bus, electrical loading, higher capacitance, and also higher resistance, but higher capacitance is very important. And that higher capacitance and higher resistance clearly leads to lower frequency over time. So you cannot easily make a very extremely high frequency bus by keeping on adding links. And clearly this goes against the scalability, right? Because if you really want to have high bandwidth, which you really want as you keep adding nodes, you're not getting higher bandwidth as you keep adding nodes in this case, because you have more electrical loading. So this is not a good design if you want higher scalability, clearly. Hopefully this makes sense. So to overcome this, people have proposed, while keeping the bus substrate, people have proposed, for example, pipelining the bus or partitioning the bus somehow, buffering it over here, or having hierarchy in terms of buses. Now it becomes looking more like trees, actually, as we will see later on. But you could do all those sorts of things. But it becomes a different topology, either hierarchical bus or tree. Okay, any questions? So hopefully this is the boring one. So this is the other extreme. If you find another extreme, let me know. But this is the other extreme where every node is connected to every other with direct, isolated, or dedicated links. And clearly this is one example. Node 0 is connected to every other node 1 through 7. That's true for node 1 also. That's true for node 2. That's true for node 3. And you keep doing this, and you have a mess in your hand. It's beautiful. But, and clearly this has the lowest contention possible, because if you want to communicate between nodes 0 and 5, you directly communicate with that. So the diameter, as you can see over here, is 1. Potentially it's the lowest latency also, if you can design this. And this is really the ideal network if cost is really not an issue and implementation complexity is not an issue. But clearly this has the highest cost, because if you look at the number of connections and ports from a node, it's ON, which is bad to begin with, because if you look at the bus, it's O1, right? Whereas if you look at the number of links, it's actually even worse, because it's now quadratic. You have ON square links over here. Okay, so it's basically not scalable. I'm not even going into the details of how you could actually potentially lay out all of these links, right? Because if you actually are building on a real chip, and even a single chip, if you have thousands of, let's say 1,000 nodes, this is not going to be possible, because how do you lay out all of these things, right? Let's assume that you have only 10 metal layers on the chip. Even with 10 metal layers, you're not going to be able to cross all of these. So you need to do something really fancy, and probably you will go crazy while doing it. Okay. That's why, I guess there's a point over here. That's why this is not used. Of course, in a small scale system, you could imagine something like this. But in a small scale system, you don't have the contention problem to begin with. Okay. So crossbar is essentially something in the middle. Let's say we picked a point in the middle. It's still costly. Basically, in a crossbar, it looks like this, and you can guess how it works. Every node is connected to every other. But now you have a shared link for each destination, and that makes all the difference compared to this. Right. Here, you don't have any shared link. Everybody's independently connected to every destination. Here, every destination has a shared link across every source, from every source. Right. Basically, if node 7 wants to send something to, let's say, bank 0, it goes through this shared link. If node 1 wants to send something to bank 0, it goes through that shared link also. So there is some contention on the shared link, clearly. But if node 7 wants to send something to bank 7 and node 1 wants to send something to bank 4, they can do that concurrently without disturbing each other. In fact, 8 things that are going to 8 different banks can be done concurrently, completely concurrently, right? In this case. So these are actually very good fit for processor and bank interconnects, or cache bank interconnects. That's true for memory also potentially, but DRAM is a little bit different. But if you look at on-chip interconnects, it's a very good fit for a small-scale connection between cores and cache banks. Okay, so clearly there's more contention than point-to-point. And as I said, enables the concurrent transfers to non-conflicting destinations. So if you have 2 different destinations, no problem. You can have completely concurrent access. It could be cost effective for a small number of nodes, and because it leads to low latency and high throughput. But of course, it's still expensive, right? If you look at the cost, it's still ON square over here. It's a different constant over here, but it's still ON square. So it's not as bad as the point-to-point. And it becomes difficult to arbitrate as n increases, because you have a shared link to the destination, and as n increases over here, arbitration becomes difficult. You can see the arbiter over here as a mux over here, right? It could be a mux of 8 things that are coming, but you may need to buffer things. We will see actually whether you build this buffered and bufferless. So now topology is going to mix with routing and buffering decisions a little bit. But you need to make buffering and routing decisions over here also. Okay, so this is actually used in real systems, used in core-to-cache bank networks in a bunch of existing multi-core processors. Although people have started moving into, as the multi-core system started scaling, people start moving into rings right now, and more hierarchical rings. But I will show you an example over here. But before we go into the real example, let's look at how to build crossbars. So it's another way of looking at the crossbar over here. These are, let's say, banks, destination nodes, and these are the source nodes. And this is the shared destination link. The question is, when the source nodes want to transmit to the same destination link, which one gets which one wins the arbitration, right? You can think of this as a bus, so you can build a bus-like arbiter in the end, right? That's the idea basically. So arbitration is something that we're going to touch on, but not cover in a lot of detail. But I'll give you an example over here. So for example, here, there needs to be some arbitration logic that decides which one loads the destination link, right? And if you don't have any buffering, you need to somehow do this design, maybe by sensing, for example, because if maybe these basically need to put out requests, and somehow you sense the requests, and some circuitry decides, okay, node 3 wins, and node 3 is the only one that can load its data onto the shared link. So you can think of this as a tri-state buffer. A tri-state buffer means you can actually load, if you've seen in digital circuits, the input is passed to the output only if this enable signal is set to 1. Right? Normally that enable signal is set to Z, meaning that output is disconnected from the input. And the arbiter decides which input, which tri-state buffer's enable signal is set to 1. That's the job of the arbiter. So arbitration becomes a problem. Clearly with 8 nodes it may not be that bad, but if you make this 10,000 nodes, then your arbitration is your complexity bottleneck. Right? Okay. But this is actually used. As you can see, there is actually arbitration that's shown over here. This is a picture from UltraSpark T2, which is an early multi-core design. It's actually Sun's early multi-core design. It's not the first design. It's not Niagara, which is one of the earliest multi-core designs actually. This is Niagara 2, where they actually made different design decisions. Basically, you have cores over here, 8 cores. You have 8 cache banks, L2 banks. There's also a non-cacheable unit, as you can see. So it's an 8 to 9 crossbar, I think. This crossbar provides a high bandwidth interface between them, and you can see that arbitration, they made the design decision to have a buffered arbiter, and the buffer size they have 2 deep queue essentially in the buffer. Basically they can buffer 2 requests, I think, for each source destination pair to hold the data transfer request, and there's a 4-stage pipeline for arbitration. So it's not done easily. It's basically you need to request, and there's arbitration, and arbiter decides which one gets to send the request to the shared destination link, and in the next cycle the transmission happens. So it's a 4-cycle latency to go over the network basically. And you can see, but conceptually it's very similar to what I've shown you earlier, right? You have the core. Every core is connected to these 2-bit or two buffers, 2 packet buffers. And then this is the arbiter design pictorially demonstrated, right? There's some arbiter that looks at basically each of these buffers and decides which one actually goes to the bank. And you have one arbiter for each bank because there's a shared link, destination link for each bank, as you can see, and one for the non-cacheable unit also. And you have something similar going back also, because you need to deliver messages from bank to cores, and you have a similar crossbar going back. Make sense? And this exists. You can read about it in more detail if you're interested in Sun's publications. Okay, you have a choice. This was a buffered crossbar actually. Now you have buffering. If you have buffering, arbitration becomes a little bit easier actually. If you don't have buffering, like what I'm going to show you over here, arbitration becomes a bit harder. Here, this is a bufferless crossbar. Basically, you need to somehow detect who is going to send a request to this red one, and the green one, and the yellow one and the green one and the blue one separately, of course, right? Now the difficulty, of course, is multiple of these nodes may actually need to send packets, and you need to ensure that only one of them can send packets, right? But you don't have any buffers. Because you don't have any buffers, these just cannot say, okay, I'm going to send the packet and arbiter handle it. So there needs to be actually tighter integration between what's here and what's here. So before this node can send the packet, arbitration needs to happen, and that has to happen in some way clearly, right? And we will discuss bufferless designs later on, but bufferless crossbars are nice. They're not easy to build. If you build the arbitration, it's very beautiful. Okay, but a buffered crossbar has more complexity, as you can see. So a bufferless crossbar, the main complexity is really arbitration. Who wins over here? And I think you can do this in different ways. Again, we're not going to go into detail, but sensing is one way potentially. Not easy, but doable. It's doable with small number of nodes. As you scale up, you may need something different. But having buffering is a completely different decision. If you have buffering now, you ease the decision of arbitration. In the sense that these nodes are actually free of arbitration. They can basically send their requests to the buffers, and the requests are over here buffered, and you can build a specialized arbiter that looks at the heads of the buffers, for example, right? Or you could actually make that hierarchical as well. So actually this arbiter is potentially simpler to design, but now you have basically scheduling is another form of arbitration. But now you have other headaches, right? Actually, there's another benefit before we go into the headaches of this. There's another benefit if you have buffering. You can have efficient support for variable size packets, right? If your packets are very different from each other in terms of their size, you can do that arbitration nicely over here. You can do it on packet basis. You can do it in different granularities. Whereas in Bufferless, you don't have a choice, right? You basically send, so for example here you can decide a large packet gets priority and gets sent, and then a small packet goes, or vice versa. Here, your basically arbitration granularity is really the granularity of the data that you're sending on this physical link. That's it. Because you don't have any other information. Okay, so these are the upsides of buffered crossbars. Buffering actually helps some of things, but of course now you require n-square buffers to do the arbitration, right? Now this is also good for performance because now you can actually load the network, put a lot of stuff, and the cores may make progress actually independently, potentially. So there's an upside in terms of performance, but buffering actually adds this complexity of buffers, but also adds another complexity of flow control. Meaning, how do you ensure that you don't oversubscribe the buffers, right? Now you have buffers in the system, and this node, for example, wants to actually keep sending messages to the red destination, and it wants to send 1,000, but it has only 4 buffers. So you need to have a flow control mechanism that tells this node, please don't send any more messages, right? And there's clearly overhead associated with that flow control mechanism because if you don't do it right, you may actually oversubscribe and you get incorrect execution. But if you do it right, you may actually underutilize some of your buffers because there's some communication latency here between here and here. And if you actually are too late in saying that I'm full, maybe there's already a packet that's sent over here, right? So you need to be careful in terms of how you do this flow control, and this leads to a lot of complexity in buffered designs in general. Okay, so now I mixed a little bit of topology and buffering and flow control, and you can see that how potentially how integrated they are with each other. But they are orthogonal, as you can see in this case. You can choose buffering or not buffering in the same topology. Okay, any questions? Okay, so now let's cover some more topologies then. Basically, crossbar is nice, but it's still not scalable enough because it's costly. Then the key question is, can we get lower cost than a crossbar yet still have low contention compared to a bus? We don't want bus. Buses are out of the question, but we also don't want crossbars. So what is in the middle ground? So people have developed the idea of multi-stage networks for this purpose, essentially. These are mainly developed for processor memory interconnections, but processor bank interconnects are essentially the same thing. And there are many variations of it. Basically, this is an example Omega network over here. You can read the details of it. But basically, these are indirect networks with multiple layers of switches between terminals and nodes. So you have endpoints, or I could have said endpoints easily over here. You have endpoints. You have multiple layers of switches in between the endpoints. And they're called logarithmic networks because their latency and cost usually scales with log n, where n is the number of nodes that you have in each side over here. You can see that we have 8 over here, and log n is 3, so you have 3 stages, right? And there's a reason for it because we actually built these switches from 2 by 2 switches, and that's why you get the log n behavior. In the end, you'll get a log behavior, but the base of the log will be the radix of the network, radix of the switches, right? If the switch is 16, then you have log 16, log base 16n, right? Okay, so that's the latency. Clearly, latency is obvious once you look over here. With a 2 by 2 switch, you get 3 layers, if you will. And the cost is all n log n here, because you have n over here, or the order of n switches over here, and log n stages. And the name multistage comes because you have multiple stages, clearly, right? So hopefully it's obvious at this point. Now the question is, where do they differ over here? I'm not going to go into details of how these are built, but they essentially differ in how these switches are wired with each other. What those switches look like, how they're wired with each other. Omega network has a special way of wiring switches. It's different from Butterfly that you've seen actually. But there's also Benes, Banyan, a bunch of different networks, and people actually had heated arguments in the past as to which network is better. And clearly you can analyze these mathematically, assuming some access patterns, and people have done that in the 70s, 80s, 90s. It's not as interesting anymore because people are more workload focused today, and really what your workload characteristics and access patterns are what matters in the end. But this is good to know in the end. Let's take a look at one characteristic of this network. Clearly, if you're here, processor 7 wants to send a message to bank 7, you have only one path, clearly, right? And you have to ensure that you go through that path. Now the unlucky thing is, if this is processor 1 sending a message to bank 6, these two conflict with each other, right? I think this also has one path. Yes, you can see that there's only one path going here. And if these two messages arrive at the switch at the same time, then they conflict with each other. So you didn't eliminate all the conflicts clearly. Well, first of all, you didn't eliminate all the conflicts to 111, but we introduced additional conflicts to otherwise different destinations, right? By reducing cost, we reduce some interconnections, and as a result, we increase the conflict rate. Hopefully that makes sense. That's very fundamental also, right? You cannot get something for free if you're reducing interconnections. So this is less costly, but your conflict rate increases. Makes sense, right? You wouldn't get this in a crossbar. You would get this in a crossbar if both are going to 111. But here, both are not going to 111. One is going to a different destination, right? Okay. Actually, you could potentially get a conflict depending on how you do the routing. Here, even though a destination is here, another destination is here, right? Makes sense, right? Because both of them go through this router to go over here. One of them needs to go over here, and one of them needs to go over here. You could potentially get that conflict. Okay, I'm going to let you answer the blocking or non-blocking question, but this is essentially a blocking network. Okay, so let me give you another example of a different design choice. So this is a multi-stage network. This is actually Butterfly. This is a different example. You can see the connections are this way. Clearly, as I said, a multi-stage network has more restrictions on feasible concurrent transaction and transmitter-receiver pairs versus a crossbar. That's hopefully obvious. But it is more scalable than a crossbar in cost. Basically, you get all n log n in many of these networks, as opposed to n square. And that's why it's more scalable. But people, when they build actually a processor to cache networks in existing multi-core systems, because they're on-chip networks, actually, that additional benefit coming from n log n is not very important in general. A lot of these interconnection networks, when they were designed for off-chip communications, actually, because the integration was not at the stage where we are at this point. So basically, these were different chips. All these were different chips, actually. Today, all of this is on the same chip, right? Then this n log n versus n squared doesn't matter as much in the implementation, because the implementation or the additional conflict rate that you get over here may not be as acceptable, right? Okay, so I wanted to make a different point over here actually, which is written over here. So you could actually have a multi-stage network, and the routing decision and the flow control decision is again independent of the network that you build over here. So for example, a circuit switch network. Do people know about circuit switching here? Yes? No? Okay, some people do. Circuit switching is basically whenever you want to transmit a message from a source to a destination, you set up a circuit, meaning set up a path. You basically go through the routers and prime them and tell them, I'm going to send a message from here to here, and set up your connections that way. And that circuit is isolated for that communication, and only when the circuit is broken, the switches are reconfigured. Make sense? Basically, for example, let's assume that we want to go from 0 to, I guess 0 is easy. 0 to 7, let's do that. If you want to go from 0 to 7, you first set up the circuit, meaning that you send an overhead message saying, set up the circuit for me. What that overhead message or control message does is, it basically sets up this router to connect this input to this input. So that communication goes from here to here, right? And during the course of that communication, you cannot go from here to here, because you actually already set up the circuit. So that communication is disabled. That's the downside of the circuit switching. Okay, that control message also sets up the circuit such that this in this router, this top input is connected to the bottom input, always while the circuit is set up. And then that message also sets up the circuit such that this top input is connected to this bottom input in this router. So now we have set up a circuit such that whenever you send a message from 0 to 7, the routers are already pre-configured to deliver that message seamlessly this way without doing additional switching. The idea is you've already set up the path, set up those connections, and the routers are not going to question that connection again until you tear down that connection. Meaning you have very little overhead in terms of switching while you keep sending messages from 0 to 7, right? Because there's no need to actually, for the router to make a decision, oh, I got a message, where should I send? No, that's already done. You've already pre-configured the routers. Basically, the router says, okay, the router doesn't even need to do anything because the switches are set up such that the message just flows through the network. So it's like almost like a direct link in an indirect, clearly indirect network, right? You set up this direct link, you minimize the routing overhead, and the hope is that the routing overhead is so minimal that your connection is just smooth like a direct link. That's the beauty of a circuit switch, essentially. You set up that direct link so your communication is very efficient, and this is very useful if you're sending, let's say, a gigabyte, for example, from this node to that destination, right? Because you don't want to go through, let's assume that the routing granularity is 64 bits. You don't want each of the routers to make the same decision again and again and again and again every time. If you're sending a gigabyte, I like doing these calculations, it's 2 to the 33 bytes, right? No, 2 to the 30 bytes, sorry. 2 to the 30 bytes, and if your switching granularity is 64 bits, it's 8 bytes. So you basically divide 2 to the 30 with 2 to the 8, that's 2 to the 22. So you basically save 2 to the 22 minus 1 switching decisions. That's a lot, right? And that's why people actually do circuit switching whenever you want to communicate streaming data between a source and a destination. That way you don't need to make the decision every time you do the routing. Okay, because you basically get rid of the routing in that case after you set up the circuit. Makes sense, right? I like abstracting this as creating a direct link between a source and destination pair in a network that doesn't have direct links in the end. Of course, the downside is now once you set up the circuit, this poor node cannot transfer anything, right? It's stuck. So you need to be very careful when you set up circuits. You lost some flexibility by creating that direct link, because you cannot create a direct link. Actually, you can. Sorry, I actually take that back. This node cannot transfer anything over here. This node can transfer something over here, right? But that may not be enough. You can only go to here, here, and here, probably, right? You cannot go down basically because of the way these switches are wired. So it's not as bad as what I said. Because you have a 2x2 switch, you can set up the switch this way, and the switch can continue transmitting this way. But you basically hampered the flexibility that you have in the network. So if you want complete flexibility, circuit switching is really not a good option. Then you basically do packet switching. And the idea of packet switching is essentially different. In this case, it's buffered packet switching, but buffering and not buffering is actually orthogonal to packet switching also. But basically, the idea is packets hop from router to router pending availability of the next required switch and buffer. And the router makes the routing decision every cycle. Right. Here, for example, assuming that in a cycle you get a message from 0, you get a packet from both 0 and 1, and the router makes a routing decision. Right. And makes the routing decision, for example, if both of them want this destination, it basically arbitrates and selects only one of them to go this way. Right. Makes sense, right? And if both of them actually are going to the lower half of the destination, it has to do that way. Because if you send the message over here, too bad. You're done now, because you cannot go back to down here. Because there's no back routing in this network, actually. It's a forward network. Actually, I guess you could do the back routing, but it becomes very complicated. Okay. Usually a separate network is used for that purpose. Okay, basically the advantage of packet switching is essentially you can make dynamic decisions for every single packet, and you have more flexibility, and you can resolve the contention right at the time it arises, right? And it can make very quick contention resolution decisions. Whereas with circuit switching, if you already set up a circuit over here, if someone else wants to request this, you have to wait until that circuit is torn down first, which could be a while. Okay. Okay, so let's go into a little bit more detail into the analysis of this. Essentially, a circuit switching. This is an aside in a sense, because we were talking about topology, but this is a good place to introduce these concepts also, because this will come again when we talk about on-chip networks. And in on-chip networks, when you're communicating streaming data, it's a good idea to do circuit switching. Actually, I actually mentioned when I talked about the heterogeneous computing systems lecture, we said that one of the systems that are designed, the Tylera on-chip network, has 5 different on-chip networks, right? One of them is for streaming communication between nodes, and that is actually circuit switched. So that was a circuit switch network. Everything else is packet switched, but the one that's dedicated to for streaming communication between nodes is circuit switched. And for good reason. Basically, okay, let's go into back to the fundamentals over here. Circuit switching sets up full path before transmission, so that the transmission happens like a direct link. You establish the route and then send the data. And no one else can use those links while the circuit is set, because it's essentially a direct link. It's actually a very good abstraction. Direct link between nodes X and Y. No one else has access to that link. Okay, packet switching on the other end routes per packet in each router. You route each packet individually, possibly via different paths. Depending on your topology, you have freedom, more freedom or less freedom in terms of which paths you can use. If the link is free, any packet can use it. So that's the beauty of it. It's very flexible. Okay, let's go back over here. But because of that flexibility, it has higher arbitration overhead. Here it's faster arbitration. Once you do the setup, the arbitration is free actually, because it's a direct link. There's no buffering. Actually, circuit switching is compatible with having no buffering. There's no real need for buffering in this case because it's a direct link. You may want to buffer at the beginning nodes clearly, or the endpoints where you send stuff, because you don't know whether you're going to establish the link clearly. But there's buffering inside a core in general normally, so there's no problem. But there's no buffering inside the network in this case, if you're operating only using circuit switching. But of course the downside is now you need to set up and bring down the path, and that takes time. There's some handshake protocol that you need to ensure, and you need to ensure that it works before you can start sending data. Packet switching, on the other hand, it has the disadvantage of being potentially slower, because you must dynamically switch every cycle. You need buffering, although we're going to deconstruct that. This was people were maybe obsessed too much with buffering in the past. But buffering, of course, helps in general. Buffering helps you to think things, but it's not necessarily good for energy efficiency. But of course, the big upside is you have flexibility, of course. I don't know if I have that on the slide. I will have it, I think. But you have no setup or bring down time. You don't need to do that. You can just send the packet and the router deals with it somehow. And it's more flexible because of that, because every single cycle you can send something and the router will deal with it somehow, right? Basically, you don't underutilize the links. Whereas here, you will underutilize the links, because if you go back to this picture over here, you set up the circuit over here. This poor node is now starved if it's going to access here, right? Even though there are links available, right? Even these links may be made available, it cannot use them because the circuit is preventing it from using them, right? Okay. Okay, so essentially it provides isolation to the streaming transfers, clearly, at the expense of other transfers that may go on. So you'll need to be very careful when you set up a circuit. Okay, so switching versus topology. I think I'll take a break right after this before we go into... Actually, maybe I'll finish... Okay, maybe before we go into the next networks, because it's going to be fun finishing topology. But basically, switching versus topology are different choices, clearly, right? Circuit and packet switching. These are methods for flow control, I will say. The choice is really independent of the topology. Any topology can be circuit switched or packet switched in the end. So it's a higher level protocol on how a message gets sent to a destination, but some topologies may be more amenable to circuit versus packet switching. For example, in the previous topology that I showed you, the butterfly network, circuit switching is good, but it will underutilize your links significantly. If you have a mesh, for example, you have a lot more freedom potentially in terms of how you set up the circuits. Okay, this is a good place to take a break probably. Otherwise I will go on and on the topology. So let's get back at 135. I guess we can restart. Oh, we're starting late. Fine. Okay, so we're done with circuit and packet switching, and we're going to continue our exploration of some of the topologies. Now here's another topology. This is actually older than many other topologies, and this is the delta network. Again, I'm not going to go through the properties of these multi-stage interconnection networks. This is an 8x8 delta network. It's different from Omega. It's different from Butterfly because of the connections you can see. And I mentioned this because it's one of the earliest papers, and this is one of the recommended papers. I would definitely recommend it. Janak Patel, who's a retired professor right now at Illinois. You remember this name probably from the MESI protocols. But before he was looking at MESI protocols, he was actually looking at the interconnection networks also, or while doing that also. And I would recommend this paper because it's a beautifully written paper about a particular multi-stage interconnection network called delta network. And here, I think one of the differences over here is each stage here has different routers, which is interesting. And you have a single path from source to destination. And it was one of the first networks that was proposed to replace those costly crossbars as processor memory interconnect. Okay, another one you've seen already, it's the Omega network. It also has single path from source to destination. But here all stages are the same actually. You can see that. It's used in NYU Ultra Computer. It's actually one of the big parallel computer building projects that was happening in 1980s. And I like this one because of what we're going to describe in the next slide. But they decided to develop this multi-stage interconnection network between processors and memories that they're communicating with. And they want to have a scalable system. And you can read this paper for more detail. But one of the things they did interestingly in this network as early as that time was actually do some computation in the network also. While the messages are being transferred, you know what kind of operation is coming in, and you could combine multiple operations on a shared memory location. This is nice, because this can help in synchronization. So you can have a synchronization primitive that's like this. Basically, let's assume that you're trying to implement a lock, right? And test and set is one primitive to help computers to synchronize. What you do is you basically load a memory location and test the memory location and set the memory location to true, basically. That's the idea. And this could be translated to fetch and OR, essentially. And you can read the details in the paper. There's also fetch and AND, depending on what you want to do, how you exactly implement test and set. But basically, while this memory location is traveling from the source to the destination, maybe different messages may be going there to operate on that memory location. Let's say, I like the idea of increment actually. Test and set, we haven't been exposed to as much, you can read the paper. But let's assume that you're incrementing a shared variable, and everybody wants to increment the shared variable. Now you don't need to bring the shared variable all the way into the processor itself. But while the shared variable is being fetched from memory and getting traversed, while it's traversing and going to one of the sources that requested, for example, what might happen is these sources that request that message may actually encounter that shared variable while it's being transferred in a switch, and they basically operate on that shared variable, right? So for example, if everybody wants to increment that shared variable, everybody sends an increment message in the network going to that shared variable, and the shared variable is being fetched, and somehow those increments meet the shared variable in the routers, and those increments get applied to that shared variable while the shared variable is actually being fetched. Does that make sense? Because you have a copy of the shared variable that's coming from memory and it's being updated. That's the idea of the combining network operation, combining fetch and add, for example. Yeah. Basically, these switches combine these fetch and add operations in the ultra computer. Basically, the idea is having this operation, fetch and add, you return m, and you replace m with m plus I. That's the idea. This actually helps with synchronization also. Let me give you one example. We talked about task partitioning, right? We actually talked about a book, for example, and you have 100 processors, and you have 1,000 pages, right? Each processor is supposed to get some chunk that's equivalent to 10 pages, right? Now your shared variable is initially 0, which is the beginning of the page, the index of the book. And everybody wants to fetch and add. They want to fetch the index and increment the index by 10. because they want to get that index beginning from what they fetched and 10 pages after that. And everybody else should see, now you do this fetch and add. Now you know that you have those 10 pages, and you increment the shared variable by 10 so that the next person who does the fetch and add sees that they get the next 10 pages. Right? So this is how you can actually get the tasks that you want from something that whose size that you know, let's say, and something from something that you know what kind of a chunk you're going to take. This works very well with arrays, of course, right? Now we are considering the book as an array. So all of the processors does the fetch and add to the index, and that index apparently magically gets distributed to the processors that need it that way. And that happens based on how that index travels over the network clearly. So it's very powerful in that sense. So it's not just test and set, it's also fetch and add, which is a general primitive. So basically, this is common when parallel processors modify a shared variable, for example, when they're obtaining a chunk of the array, and this is how they get the chunk of the array. And they don't necessarily need to obtain an equal sized chunk this way, right? They can say, I want the index of the array, and I want to increment the index by, let's say, 58. So that the next processor who wants the index of the array gets m plus 58. Right? That's the idea. So everybody can get a different chunk this way. And this paper actually talks about how they implement it in their network and how it actually improves their synchronization, especially when these tasks are distributed, or especially when you have contention in the network for this sort of shared variables. So that's a nice idea that I think is relatively ahead of its time, as you can see, right? It's 1980s, and you're already integrating computation with communication here. While we're communicating the shared variable, why don't we also operate on it? Right? So it's very synergistic with processing in-memory concepts, I think. Okay, so the combining clearly reduces synchronization latency because every processor doesn't need to go and update the data separately. This happens in the network. Okay, any questions? Okay, you can read for more detail in this paper. So let's talk about some other networks. So we can go on and on in terms of multi-stage networks. This is the last one I'm going to examine. This is Butterfly. It's very nice. Basically, it's also used in real systems, and this is an example where you may actually get conflicts if you have a lot of contention, but it's not necessarily restricted to Butterfly actually. These conflicts happen in all of the multi-stage networks. But basically, in Butterfly you have some flexibility. You can actually randomize the route a little bit. But of course you need to be careful because you cannot randomize it completely. Here you have a lot of flexibility, right? Basically, you can go down here, but and you can go up. But you basically can play some tricks in terms of randomizing the routes over here. But I'm not going to go into detail of it. So let me review some of the topologies that we looked at. Basically, it's not all, but we have Crossbar, multi-stage logarithmic, and mesh. We're going to look at soon, but we've kind of looked at it. And you can classify these as indirect clearly, and this is direct. Blocking, non-blocking, you can learn about it yourself, but this is non-blocking. This is the only non-blocking one over here. Crossed, as you can see over here, is interesting. This is ON square, this is ON log n, and mesh is going to be ON actually, which is going to be better in the end. And latency is going to be not so good though. Basically here latency is O1 with single destination. Over here it's the arbitration latency. Here it's O log n, and here it's going to be O square root of n. Okay, but we're going to build the mesh after we talk about the rings. Okay, so now as I mentioned that we're going to go back to simple again, right? So this is a bit complicated. We started from bus, we made it more complicated, point to point. We said point to point is not really desirable, so we get to crossbar, which is closer to point clearly. And then we moved into multi-stage logarithmic. We're going to move to mesh, but let's also ask the question, let's go back to and revisit the bus a little bit. Can you actually make the bus a little bit more scalable? And I think this brings us to the ring a little bit. Although it's a completely different topology, you don't have a single link, but you have a single logical link that's partitioned between nodes. That's the way I like to think about a ring. Basically, each node is connected to exactly two other nodes in this case, and nodes form a continuous pathway such that any packet can reach any node in this case. So in that sense, it's very similar to a bus, right? Virtually, it kind of looks like a bus. But it's really partitioned completely. You don't have a shared communication medium. That's the big difference. Basically, it's partitioned in a very special way. Each end node actually has a connection or part of the bus that connects each other. Right. Okay. So hopefully you've seen rings before. But basically, if you want to communicate between this node and this node, you basically need to go through multiple hops over here. If you have a bidirectional ring, you can go through this way also. Right? So you can actually have multiple directions over here. So this is cheap in this case. The cost is ON because you have n number of links. It's the same number of links as the nodes. But of course, latency is a problem here, right? Latency is still ON. As you keep adding nodes, you keep adding links, and it's also not easy to scale, right? And this is actually a case where bisection bandwidth is interesting. Here you look at the bisection bandwidth. How do you define the bisection bandwidth? If you remember, it's not the greatest metric, but here it makes sense. But basically, what you do is you cut the network in half. It's easy to cut the network in half here, and you sever links, and you have two links that are severed here, and you calculate the throughput of those links. As you keep adding nodes, that bisection bandwidth stays constant, right? Unless you increase the links, of course, right? But assume that you don't increase the links. You keep adding nodes to this, nothing changes. The ring is still a ring, right? And you basically keep adding nodes on it. So basically, that's the bandwidth bottleneck. Essentially, a ring becomes a bandwidth bottleneck as you keep adding nodes. Actually, you can do the same thing in a bus, and you will see the same thing. In a bus, you have a single medium, single link. Bisection bandwidth, you cut it in half, and then you have, anyway. You basically are not scalable in the end. Make sense? Okay. But this is actually beautiful because this is easy to build. It's very easy to build. And as a result, it's used in a lot of existing multi-core processors. Actually, one of the IBM Cell, it's the earliest heterogeneous multi-core, had a ring to communicate between different processors. Like Intel Larrabee, I mentioned that this was Intel's effort to actually build a very fine-grained multi-threaded engine that's massively parallel. And they had actually a ring. In fact, they had a bufferless ring that didn't have any buffering in the ring itself, which we will talk about. And many commercial systems use it today. Of course, not in the exact same way that we're going to see over here, because if you want to scale up to 64 nodes, you really don't want to go through every single node or some number of nodes to communicate with some other node, right? Okay. So let's talk about the ring a little bit more before we make it more complicated. Essentially, this is a unidirectional ring, which means that you have a single directional pathway. You can go from only left to right, let's say, or clockwise in this case, or counterclockwise. And these are the routers that we have, and these are the nodes. Basically, the nodes need to connect to the link with some sort of router, right? And that's essentially the 2x2 router that we've been seeing before. So why do you need this? Essentially, you need to be able to inject into the ring, and that's how this happens. And you need to be able to eject from the ring, right? So if this is the destination, the ring, this router actually provides the data into the node, and if this is the source, this router also provides the data from the node into the ring, which hopefully makes sense, right? Of course, the design of this router may become more complicated now, and if you really want to be energy efficient, you want to optimize the design of that router. Okay, so clearly this is simple. It's a very simple topology, and the implementation is also very simple. It's easy to lay out this thing, and you get reasonable performance if n is relatively low, and the performance needs are also relatively low. Basically, your bandwidth and latency. Because latency is problematic here, again, right? If you actually have only 4 nodes, the latency of this is potentially higher than the latency of a bus, right? Bus is a shared medium. But of course, the bandwidth of this may be higher than a bus. Okay, we discussed that it's ON cost, average hops is n over 2, and latency depends on utilization. I'm not going to go over this in detail. Any questions? Okay, so of course, unidirectional ring is one directional, and you can get bad effects like this node, when it wants to communicate with this node, it has to go through every other node, right? Doesn't sound good. Whereas if you had some other direction this way, bidirectional, then you could have balanced the load better. and reduce the latency as well. So basically you provide multi-directional pathways. You can consider these as multiple rings also, and they're essentially multiple rings. One is going this way and the other is going this way. And this reduces latency clearly, because now this average latency reduces, and this node can communicate with this node. And maximum latency also reduces. Maximum latency is now n divided by 2, right, as opposed to n. But of course now you have a more slightly complex additional hardware cost. Your injection policy is also complex, right? You need to select which ring you need to inject the packet into. Right? So basically you have a decision. You don't have just this ring, but you have another router over here attached to another ring. You have to pick which ring you inject into. Right? And all of the problems exist, like load balancing, which we've been talking about many times in this lecture. But you can take advantage of that better, hopefully. Okay, any questions? Okay, then the question is, this is a nice topology, how do you scale up? And I like actually rings a lot, because once you start building hierarchy into rings, they become very scalable. You can actually build hierarchy into any of the topologies that we discussed, right? You can have a small piece of your processor connected via bus, and let's assume that 4 processors are connected via bus, and you have 4 processor clusters connected via a ring, right? That's possible, certainly. That's how you scale up. So you maximize the potential loading on the bus, n processors, and then you have a ring, and then maybe you have a mesh of rings in the end, right? Basically, you could combine topologies also. Adding hierarchy increases your scalability. Of course, it increases your complexity also, because hierarchy is also adding heterogeneity, right? But I think just with rings, you can actually add hierarchy without changing the topologies of the individual pieces of the hierarchy. So these are examples. I like these pictures. I think they're beautiful. But this is an example of different ways of building 16-node systems. So this is a 16-node system. Let's assume that you don't want a you don't want a single ring, or you don't want a single bidirectional ring. You basically have clusters of 4, and each of them is a ring over here. And there's another ring that connects those 4 rings, right? And you could actually have higher bandwidth than these, potentially, right? You could have another ring stop over here, basically. And if you're communicating locally, you don't go through that ring stop. You don't stop over there. If you're communicating between these different rings, then you need to hop onto this global ring, if you will, or the second level ring. But this is only one way of building. The second level ring is very simple here. But you could make the second level ring even more complicated, as you can see over here. Maybe add more bandwidth, add more points. This could reduce the latency potentially, right? Or you could have multiple rings, multiple second level rings. So there are different ways of building it, actually. This becomes very creative, I think. And I like rings because they're very simple and they're very energy efficient. I'm going to point you to some papers that show that their energy efficiency is actually really nice. But of course, if you really want to maximize your energy efficiency, you want to localize your communication as much as possible. But you knew that before, right? You don't want to move data. You don't want to move stuff in general. You want this for scalability, but ideally you want to minimize your communication. So the upside over here of adding hierarchy is going from here to here is just 2 hops, right? Basically, if you want to communicate between here to here, you need kind of 2 hops to get to the bridge router. This is called a bridge router. And then you need 2 hops to get to this bridge router, and then you need 2 hops here, right? So it's basically 6 hops over here. Basically, you can reduce the latency significantly over here. But of course, if this is a bus, it's even better potentially. But we're not going to go into that. And I believe that it's better if it's a bus in the end. So this is another example. This is a 64-node network. It's a 3-level hierarchy. That's not necessarily the best way of building it, but you can see that this is one level 1 cluster, and 4 of them are connected to a level 2 cluster with this ring, and 4 level 2 clusters are connected to each other with this ring with green ring stops. And this way you can add more scalability. You can add more, you can make the latencies lower, because actually these rings can be much faster, actually, which is interesting. But this is clearly more complex, and layout of your data starts mattering more and more. Although if it depends on your comparison point. If your comparison point is a single ring, these are all much better in terms of how you lay out your data in the end. If your comparison point is a mesh, then you need to be much more careful. And that's where the topology comparisons become difficult. Because how do you do the fair comparison, right? Because if you compare something like this to a mesh, you need to build hierarchy into the mesh also potentially. Right? But if you're interested, we've written a couple of papers on this topic. But this describes the design implementation of a mostly bufferless hierarchical ring. And this is actually an extended version of that paper, which actually shows that you can be very energy efficient in the design space of different topologies. And this is really not an easy study to do, actually, because what do you compare to? Because here you actually minimize the buffers as much as possible. If you add a lot of buffers, yes, you'll get a lot more performance potentially, but at the expense of very high energy in the end. And in today's SOCs, actually, this sort of different thinking in terms of topology and routing is very much needed, because today's SOCs don't necessarily need extremely high communication capability or very high performance. They need good enough performance when that performance is really needed, but they need extremely high energy efficiency in normal mode of operation. You don't want to dedicate all of your power budget to interconnect. Interconnect is important, but maybe not that important in the end. Okay, well, nothing is that important in the end. You don't want to dedicate any of your budget to any part of your processing, right? It's in the end your system level design choice, and you have to distribute your budget such that you get the good performance as you need. Okay, any questions on hierarchical rings? I like this topic, very fascinating actually. And I think there's more room for creativity in terms of topology design plus its combination with routing algorithm plus flow control. Okay, so we're back to the mesh basically. I've kind of defined it before, but mesh is what it looks like. It's a two-dimensional mesh over here. Each node is connected to 4 neighbors, north, east, south, west. Each node has a router associated with it, except for the edge nodes over here. Edge nodes don't have essentially neighbors on at least one side, and these corner nodes don't have neighbors on 2 sides, right? Here the cost is ON. Again, average latency is square root of n, as you can see. This is very easy to lay out on chip, so this also liked by many implementers in general, because you have regular and equal length links over here, which is very nice. You can basically lay out a piece and stamp it out, right? That's it. It's very easy. So here you get path diversity, which also existed in hierarchical rings, which also existed in bidirectional rings, which also existed in some of them. But here the path diversity is a lot, basically. Basically, there are many ways to get from one node to another, right? You can go from this node to this node this way, or some other way, right? Depending on how you do the routing. And this is used in some existing on-chip networks and on-chip network prototypes. Tylera chip that we discussed in the heterogeneous computing systems lecture, it has 100 code versions, and they have 5 different mesh networks essentially. They have very wimpy cores. Their network is actually more powerful than the cores, I would say. Okay, clearly mesh has one problem. It's not symmetric on the edges, so its performance is very sensitive to the placement of the task on the edge versus middle. So if you're here, you cannot communicate easily with this node over here. Well, I guess it becomes exacerbated as you increase the size of the mesh. So Torus essentially avoids this problem by adding links that go this way, right? Okay, that's the idea. And you have corresponding links that go this way also. Now, actually, everything is symmetric. And you get higher path diversity and also bisection bandwidth because you added more links. So when you cut the network in the middle, you sever or you cut more links, clearly. But it turns out this is a bit harder to lay out on chip because it has unequal link lengths now, right? Mesh is beautiful because you don't run into that problem. Right? So layout issues actually become more important. But of course, it's also a higher cost as clearly we're adding links. But the cost is actually not that bad because it's still ON, right? The constant differs, but it's still ON. So in terms of scalability, it's not bad. But in terms of layout, it's not good because how do you lay out these things? It's actually not that bad. You need to be just a little bit more careful. So this is actually a piece of that torus over there. You can view the nodes with each other to make internode latencies almost approximately constant, basically. This is one way of doing it. Again, I'm not going to go into detail. You can get more creative, but it's not as easy as mesh, clearly. Okay, let's talk about trees. Now we're getting a little bit more specialized. But these are also topologies that are proposed. Essentially, trees are what they are. They're trees. They look like trees. They're planar hierarchical topologies. And the benefit is that their latency is log n, O log n. And these are usually good for local traffic. That if you can map your traffic or computation nicely, such that most of your computation is localized, or communication pattern actually resembles the communication pattern of a tree, meaning you generate results over here, and then results need to propagate up, and then they need to be accumulated, for example. A lot of reduction operations are that way. Then trees are a great fit for that sort of operations, right? Maybe not the great fit for communication, general purpose communication from here to here, for example. But if you're communicating locally, aggregating data locally, and then putting up, and then aggregating data locally over there, and then putting up or sending it up, then this is a very good communication method. Actually, clock trees are like this as well, right? Clock tree, whenever you're routing the clock in a processor, it usually looks like a tree. H tree is one example over here, because you really want to minimize the clock skew, and you want to minimize the distance between where the clock is generated and the clock is delivered or used. And trees are a very good example to minimize the clock skew. And there's a lot of research in that area that I'm not going to go into. Okay, but the benefit is it's also cheap, ON cost. It's easy to lay out also because it's very regular. And it's, again, it's regular, but it's also local communication. What makes layout harder is non-local communication, right? So here it's local, as you can see, right? So here it's local, mostly local. Even though it's hierarchical structure, it's local. This is not local, right? That's the difference. That makes the layout harder. Okay. But of course, now if you actually use this as a substrate, the root of the tree can become a bottleneck. Assuming you have a root over here, all of the messages that go from this side to this side have to traverse, and vice versa, the root. And that root becomes a bottleneck. As a result, when people actually use these topologies or develop these topologies, they increase the bandwidth of the links as they go higher and higher in the hierarchy. Which makes sense, right? You have relatively less need for communication and less contention over here. As you go up, contention increases, and you commensurately increase the bandwidth. And that's why this is called a fat tree, essentially. It's fat closer to the top. And these were actually used in some parallel computers. Connection machine is an example one. This was designed by the Thinking Machines Corporation. These are actually machines that are really, really interesting. If you're interested, I would recommend studying it. But this is their fat tree, basically. You can read the paper for more detail, but it has these 4x2 switches. You have these 4 nodes that go through a 4x2 switch. And you can see that it's not just a simple tree. You can think of this as multiple trees, I think. And there are multiple routers that are going multiple trees. The reason is they want to basically have some say in the contention, right? They don't want to have a single bottleneck anywhere. Here, these 4 nodes can go through 2 different ones, as you can see, right? And they split the load. They distribute the load, basically, right? Across different routers. And this is one design. The paper talks about several different designs. And you can see that the top nodes get the traffic and distribute it down to only the left ones. So this one, for example, is responsible for only the left ones over here, and that one is also responsible for only the left ones, and these ones are responsible to the right for the right ones. Anyway, you can read for more detail. But basically, the advantage of having these is you can have randomized routing on the way up, and these folks also supported combining operations in the network. These folks also supported multicast operations with integrated support. Basically, the switches were aware of multicast, and they basically sent the operations to only those nodes that actually needed it. So multicast means you have a single node sending something to a subset of the nodes, not all of the nodes. All of the nodes would be broadcast. If a single node is sending a request to all of the nodes, it's called broadcast. If a single node is sending to a subset of nodes, it's multicast. Instead of sending a single message to everyone, you basically send a single message encoding all of those nodes, and that gets distributed. I should say it again. Instead of sending a single message to every single destination, which requires many messages, you basically send a single message that encodes those subset of nodes that you're going to communicate with, and the network handles that multicast internally. So it basically minimizes the messages that you need to send if you're doing a multicast operation. Okay, and this is a very beautiful book actually that talks about how they have built this machine. There are a lot of other interesting properties of connection machine. It is actually a bit serial computer. Basically, because they wanted to exploit the data level parallelism, what they said was, we don't care about the latency of a single add. If you remember this discussion we had, we're going to make the adder extremely simple, and the adder is going to operate on a single bit every cycle. And if you want to do a 32-bit add, you take 32 cycles. And we have so much parallelism in our data sets that, or what we want to do, that we don't care about that latency. So I think one of the versions of CM, I don't remember if it was CM5, but one of the versions, maybe it's CM2, was had 65,000 adders, 64K adders, but each adder was bit serial. It's fascinating, I think. Also, they did support reduction operation as we discussed. For example, if you go back over here, if you're adding a bunch of numbers, if you're adding an array of numbers, you basically put all of the numbers in the array in the bottom nodes, and the bottom nodes keep doing the addition, or they send it. For example, this adds 2 numbers and sends it up. This adds 2 numbers and sends it up. This adds the 2 numbers it receives and sends it up, and you keep doing this, and in the end you reduce the data over here, right? And this had actually some support for reduction operators, so that the network actually could do that internally without a lot of effort. Okay, any questions? Okay, you're not bored yet. So now we can talk about hypercube. These are some of the more complicated topologies. Essentially, this is an n-dimensional cube, or n-cube, and you can see different dimensional hypercubes over here. And these are good for latency in the end. That's why they were actually designed. And this may not look very nice, but you will see something that doesn't look, that looks even less nice maybe. But I think this is a 5-dimensional hypercube over here. Or maybe it's the same as this one. Anyway, I don't know. But basically, the latency is O log n over here, which is very nice. The radix is O log n, and the number of links is O n log n over here also. So this was designed for fast message passing. And the first time, so basically the low latency is here, but of course there's a big downside here. That's why this is not used in many processors today. It's very hard to lay out in 2D, or even 3D actually. I mean, of course, you eventually need to lay out in 3D, but you need to deal with the cables very carefully. Okay. So this was used in the Cosmic Cube. This is actually a paper that I would recommend otherwise. It's actually one of the earliest papers that talk about message passing in a real system. This was a 64-node message passing system that was built in the 1980s. And they had a lot of really interesting things, but they wanted fast delivery of messages basically. This was essentially in the times where people were arguing should we build shared memory machines versus message passing machines. This was on the message passing side essentially. There's no shared memory here. And they basically argued that our network needs to be extremely fast, and essentially they built this hypercube, and this is their hypercube. You can see that it's not easy to lay out, right? And you can easily make mistakes potentially. Anyway, I'm not going to go through this in more detail than what's described over here, but I would definitely recommend the paper if you're interested in learning about an early message passing machine. But I think this is an example also of modern supercomputers in a sense. Modern supercomputers, of course, have much more than 64 nodes. 64,000 nodes, even more, right? But essentially they have the same problem. I mean, they have to communicate with each other somehow, and they usually employ a combination of shared memory plus message passing. And they need low latencies, especially if you want to partition a problem into 64,000 nodes, and they are usually designed to solve a single problem, right? That's what a supercomputer is, actually. It's not a data center. It's a totally different thing. You can use a supercomputer as a data center, no question about that. But a supercomputer is really designed to solve a single, very difficult problem in general. And you partition that problem on many nodes, and in the end, you need to communicate between those nodes, right? And that's why your network becomes extremely important in a supercomputer. And that was one of the reasons why this computer was built. This is the supercomputer of its day. And you can see that interconnection complexity becomes not so nice to deal with. And existing supercomputer designers deal with this also, basically. If you actually, there are stories that people tell, and actually I've heard this in one of the keynotes, I think at SC once, and essentially because of misconnections that engineers or operators make when they actually set up the machine, it takes a lot of time to get the machine running. Because if you have a system like this, now you need to figure out which connection you need to put the cable to, because these are cable-based machines, right? Unless they're optical. Optical is different. These are cable-based machines, so there's a lot of wiring that you need to do, and these cables essentially interfere with each other, interfere logically with each other, because you have to route this cable from here and route this other cable from here to there, and you make a mistake, and that mistake costs a lot to actually find out first and then fix next, right? Of course, most of it is finding out in the end. So these are real issues basically that people deal with. And the interconnects that are used in existing supercomputers are sophisticated. Maybe they're not hypercube necessarily, but there are other different interconnects like Dragonfly and all of these fancy names that you will see perhaps. I'd be happy to talk about it separately, but this is where I'm going to stop, I think. But these, essentially the concept that we cover over here span across the stack. It's not just on chip. So this is maybe very difficult on chip, but this is actually not so bad potentially off chip. You just need to be careful in doing the connections. But if you go to 64,000, maybe you don't have a 6-dimensional hypercube, right? How many dimensions do you need in that one? That one I think you need to be more careful. That's why I think interconnects also become more heterogeneous as you go to many, many dimensions, right? I guess arguably internet is not a supercomputer, but it's probably the largest network that we have, and it's extremely heterogeneous, and there's no structure to it, as you can see. But it's also the case that it's very difficult to partition problems on the internet, a single problem on the internet, and utilize many machines, right? Because once you start synchronizing, you're bound by all of the latencies of the communication. Okay. Any questions? Now I'm done with topology. I could go on and on, but there are interesting topologies that we didn't cover. Okay, now let's go into routing. So routing is clearly tightly integrated with topology, but it's something different. Basically, how do you deliver a message from one source to another, one node to another node? And there are multiple different mechanisms for routing. I'll go through this relatively quickly, but this is also important because this affects your router complexity. So there's arithmetic routing. Basically here, the question is, how does the router determine where to send a packet that it gets from a source, which output port should it send the packet on, right? Arithmetic means you just need to do simple arithmetic to determine the route. So you have a regular topology, and you have an arithmetic routing mechanism where you could do very quick, simple arithmetic and decide, okay, I'm going to go from here to here. Right? So for example, if you have a mesh, I guess I have to illustrate this because I don't have a slide on it. But if you have a mesh topology, it's very amenable to arithmetic routing, assuming you restrict your routing algorithm to be arithmetic routing. Okay, so basically you number your nodes. Okay, I didn't show all the nodes over here, but let's assume that this is your node 0, 0, row 0, column 0. And this is your node 63, 63. Right? So basically, you can quickly determine whether you want to go right or left by comparing the x and y coordinates that you have, right? Here you're at 0, 0 over here, and you want to go to 63, 63, so you want to send a message to the right, clearly. And you keep doing that. At this point, at some point you reach, a commonly used routing algorithm here is called XY routing, or dimension order routing, meaning you first traverse the x direction until you get to the right y point, which is column. And how do you figure out you get to the right y point? By comparing the destination's y point, 63, to the router's y point, which is 63. If it's equal, then you start going in the right y direction, right? That's the idea. And I just did that arithmetically, right? And exactly that's what the routers do. So this dimension order routing is an arithmetic routing based mechanism. At every router, you compare the destination's xy coordinates to the router's xy coordinates, and you decide where to go. and you decide where to go based on some routing algorithm. So XY routing is one example, but you could also have YX routing, meaning you prioritize Y direction first and then go to the X direction. Right? Of course, if you have this, now you're limited to your path diversity, meaning you can have many, many paths, but you're not taking many, many paths. Right? You're just doing X and then Y, or Y and an X. Right? But your routing algorithm is very simple. Make sense? Okay. Of course, this works nicely with regular topologies, right? Okay. So the other routing algorithm is a routing mechanism type is source-based, and we've already discussed this basically. Source specifies output port for each switch in the route. So the router doesn't need to do anything here, except just switching, of course, right? Router doesn't need to do the route calculation. So here switches are simple. There's no control state. You just look at which output port you need to send this packet from. But of course now you need to have a large header, right? So if you go back to this example over here, if I pull it up, a source-based routing, basically when you inject a message from here to 6363, you basically specify exactly which route you take. For example, in this router, you take, what is this? East, right? And when you get to the next router, let's assume that you take south. When you get to this router, let's assume that you take east. When you get to this router, let's assume you take south. Let's assume you take west for whatever reason. And then south, ... right? Basically, you specify everything when you inject the message. And this leads to a very large header that encodes every single action that you need to do in the network, clearly, right? But of course, this is nice because now the router doesn't need to do anything in terms of deciding the route. But somebody needs to do something. And how do you handle contention becomes difficult in this case, right? So you need to think about the contention. So this is very nice if you have a lot of control over the system and you know what's being injected at what point, right? Because you cannot handle the case where a packet specifies, so a packet comes here and it specifies east, and another packet also comes here at the same time and also specifies east. That's not going to work. You did something wrong in your source-based routing if that happens, right? Basically, this is a very static routing scheme. It's not very applicable generally, but you could apply it in small situations potentially. Right? And the last one is table lookup based. Basically, this is the most flexible one, essentially. You basically index a table to get your output port, right? You know the destination, you know the source, and based on some information and perhaps some other information, you decide what your output port should be. So in this case, your header is small. You just need to specify what destination you're going to go to. And the router locally makes a decision based on the table lookup. And these tables can change now, right? Potentially you can reconfigure your tables. Just because every single router is now, whenever it receives a message, it's looking up a table. And based on, let's assume that the message comes here, it looks up a table. And this table says the message should go this way. For whatever reason, right? It could be that somehow this link was broken, right? So it was faulty. And you decommissioned it, and all of the messages are going that way, right? So that's the beauty of table lookup based, because you can enable such fault-tolerant routing. It's very difficult to enable fault-tolerant routing in an purely arithmetic algorithm, right? Because now your arithmetic thing has changed, right? Because you lost some routers or links. Okay, hopefully these are obvious. Any questions? But this has to be done. I mean, most existing systems use table lookup based because they need to be fault tolerant. But source based is possible also. So source based doesn't preclude fault tolerance really. As long as you detect the faults and communicate the faults to the source, there's no problem, right? Okay, so let's talk about routing algorithms, which may be even more interesting. So there are three types of routing algorithms. One is deterministic. We've already seen one example. You always choose the same path for a communicating source and destination pair. Now and the second is oblivious. You choose different paths without considering network state. So if you're communicating between X and Y, the first time you communicate, you choose one path. The next time you communicate, maybe you go through some other path. The next time, maybe you go through some other path. It's oblivious, basically. It's oblivious in the sense that it's oblivious to the network state, as we will see. Basically, it's not going to take into account the state of the network. But it's also not deterministic. Deterministic is a single path every time. What I showed you over here, XY routing is deterministic. you always go from here to here, you always go from this way, right? X, Y, X, Y, X, Y. And this is very bad, as you can see, right? If all of these nodes are communicating with that node 63, 63, everybody's going the same way. And you have a lot of congestion in the network. So deterministic usually leads to congestion. Oblivious fixes that congestion problem because going from here to here, you can maybe go through XY. You can maybe go through some random route over here, maybe here. So you have many, many paths that you can exploit that way. Of course, how do you actually decide which path becomes more complex in that case, right? Adaptive, now you can choose different paths adapting to the state of the network. So basically, you're not deterministic again, but now the path you choose, consider the congestion that's happening in the network potentially, right? So it's more adaptive in that sense. So it's in a sense it's better than oblivious, but we'll see the trade-offs in a little bit. Of course. So then there's a question of how to adapt, right? Usually there are two ways to adapt. You can look at local or global feedback. Which one do you use? For example, I guess I keep doing this, but there's no better way of handling that, I guess. It'd be nice to have some color, I guess, but let's see. Oh, we did find some color. Okay, so basically you're making a decision of where to send the packet over here, assuming that it's going to still go to this destination. Do you send it this way, or do you send it this way? You could also send it back, right? Which is not productive in that sense. So if you look at these two paths are productive because they're reducing the distance to the destination, and this path is non-productive because they're increasing the distance to the destination. Now, if you actually choose this one, then it becomes a non-minimal path, non-minimal routing. If you always are restricted to minimal routing, you have to choose between these green ones, right? So that's a choice you need to make when you're designing routing, because if you become non-minimal, you introduce some other problems, as we will see. Because how do you guarantee forward progress in the presence of non-minimal routing? Meaning that in the presence of your routing algorithm taking you farther away from the destination, right? And also local and global feedbacks. Now actually, which path do you choose? Assuming that you want to choose between the minimal paths, do you choose this one or this one? Well, you could consider the feedback in terms of how much congestion there is, right? Local feedback says, okay, maybe you consider how much congested these immediate routers are. If this router is not congested, then I go this way. If this router is not congested, then I go this way, right? Because they're all equal in that sense, right? How do you equal in terms of the hop distance sense? But you could also consider global feedback. Maybe you know information about this global area, and that's more congested, and maybe this global area is less congested, right? Or it's still local in the grand scheme of things, but it's more global than the immediate router. So if you have that more global information, then you could actually make that decision based on global information. If this is more congested, then maybe you choose this path, right? That's the idea. But of course, all of this requires keeping track of information, right? If you want to make your routing algorithm more and more sophisticated, you need to keep track of more and more information in the end. And I like, in general, the most flexible algorithms. Non-minimal adaptive algorithms are the hardest ones to design, but they're also the most flexible. Minimal adaptive ones are not the most, not the simplest ones, not the simplest algorithms. So they're adaptive, but they have this restriction of minimality, meaning you cannot go back, right? Which may not be a desirable thing, right? Why it may not be a desirable thing? I keep doing this, but if you're always minimal, let's assume that basically, if you always want to be minimal, you always want to make forward progress, meaning that you want to either decrease your x distance or decrease y distance, right? But let's assume that you have a lot of congestion. If you have a lot of congestion, you sometimes may want to route around the conflict area, right? Assume that you have a lot of congestion over here. Let's assume that this is your congested area, that green part, right? And somehow you came here. And you can go this way or this way if you restrict to the minimal algorithm that reduces your distance to the destination. But clearly this is not congested. Maybe it's if you can do non-minimal adaptive routing, you can go this way, right? And avoid a significant chunk of the congestion. I didn't draw it nicely because this should not be congested, right? That way you avoid the congestion completely. That's the idea, basically. That's why non-minimal adaptive is actually usually better than minimal adaptive. Okay. So let's examine each of these in a little bit more detail, although I've given you a lot of the trade-offs that I'm going to talk about. Essentially, deterministic routing is simple. All packets between the same source and destination pair take the same path. Dimension order routing that we examined is one example. You first traverse the x dimension and then traverse the y dimension. Right? It's called also XY routing, and this was used in early some supercomputers, and many on-chip networks actually adapt this. It's simple, it's nice, but it can lead to a lot of congestion in the end. YX routing is another example of it. Actually, you can do YX also, right? You could have a combination of XY and YX. That's also deterministic in the end. Okay, the simple, it provides you deadlock freedom. We're going to talk about this actually, meaning there is no cycles in resource allocation. So deadlock is the case where you cannot make any progress in the network because there is a circular dependence on resources. Right? In this case, if you do XY routing, you can never create a circular dependence on resources, and we will see that in a little bit actually. Because everybody's traversing through XY, so there's no way you can actually depend on something that's going backwards this way, and we will see that in a little bit. So that's a big advantage of this. In fact, you need to be careful when you're designing a routing algorithm, because if you're actually prone to deadlocks, that's going to be very hairy. Okay, but of course the downside is this could lead to high contention, as we discussed. If everybody is going from the top row to this rightmost column, let's say, and even worse to the bottom right node over here, everybody sends traffic this way, right? So you basically do not exploit path diversity. As a result, you lead to high contention and high latency also. So let's talk about deadlock. This is what I was mentioning over here. Essentially, this is no forward progress. This is the classic definition of deadlock. It's almost always caused by circular dependencies on resources. Sometimes, of course, it's caused by faults, but this is assuming a non-faulty network. It's caused by circular dependencies on resources. Basically, each packet waits for a buffer occupied by another packet downstream. So this is an example. Let's pick this example. So this packet 3 is waiting for this buffer, but packet 4 is occupying it. This packet 4 is waiting for this buffer, but packet 1 is occupying it. And packet 1 is waiting for this buffer, but packet 2 is occupying it. And packet 2 is waiting for this buffer, but packet 3 is occupying it. Right. Done. That's your deadlock. And this happened because you could create a circular dependence due to your routing algorithm. You could not create the circular dependence if all of the packets were following XY dimension. Right? X first, Y first. No, because some of the packets will not be waiting for the resources that they're waiting for in this picture, right? Because this is, for example, going this way, and that cannot happen in XY routing. That's the intuitive explanation of it, of course. So you can read more detail about this. It's actually a very fascinating topic also. But basically, how do you handle deadlock? There are multiple ways. Clearly, a routing algorithm, designing a routing algorithm nicely such that you avoid what's called these cycles, cyclic dependencies, is one way of avoiding deadlock. And I think that's a nice way of avoiding deadlock, but it's not the only way. But let's talk about this. Basically, you cannot build a circular dependency in your routing algorithm, and you do this by restricting the turns each packet can take. Actually, dimension order routing is a little bit conservative in terms of being deadlock free. You could actually have a much more aggressive routing algorithm, and that restricts just the right turns so that you don't run into deadlock. And I'm going to reference a paper in a little bit that you can read that talks about this. But basically, avoiding cycles in routing. You can avoid deadlock by adding more buffering, escape paths that are used in case of deadlock potentially. So you need to be very careful about this, but this could help. Or you could detect and break deadlock. This may not be an easy thing, right? I mean, this sort of deadlock, for example, happens when you lock things as well, right, in the software level. And detecting and breaking deadlock is not easy in general, but it's possible. You could preempt some of the buffers. So how do you break the deadlock? You could say, okay, I found deadlock somehow in my system. Maybe there is no there's no forward progress in this region for a minute, so I'm going to take action. And my action is I'm going to take some of the buffers from some of the packets and basically ask people to resend those packets later on. Right? That's one way of breaking deadlock. It's a very heavy-handed measure, but it's possible to do it. I think it's much nicer if your routing algorithm doesn't run into these issues in general. I think this is also an okay solution, but this increases your complexity in general, and you need to be careful about it. So how do you design a routing algorithm that avoids this by construction? Then I think you need to go into more theory of routing in general. But basically this paper is a seminal paper that talks about how to do this in one way. It's called the turn model for adaptive routing. The idea is very simple. You analyze directions in which packets can turn in the network. Turn meaning you go from x direction to y direction in a two-dimensional network, clearly, right? Or y to x, right? You determine the cycles that such turns can form, and you prohibit just enough turns to break possible cycles. You eliminate all the possible cycles. And you can see this paper. You can see that the possible turns and simple cycles in a two-dimensional mesh. You can see that clearly topology makes a big has an effect on this. We're talking about meshes over here. Meshes are simple actually. If you go into more sophisticated topologies, you may actually run into deadlocks in different ways. And these are the 4 turns allowed by the XY routing algorithm. And you can see that if you allow 6 turns, then you'll lead to deadlock. And you can read the paper for more detail. Okay. Any questions? Okay, these are correctness issues, but they affect your performance also, because if you solve your correctness issue in a very conservative way, like XY routing, I think your performance goes down significantly, especially in cases where you have contention. Okay, so this is deterministic routing. Deadlock is actually present, especially in deterministic routing, but it's not necessarily limited to deterministic routing. Oblivious routing is another idea, and the most commonly known algorithm here is Valiant's algorithm, and I recommend taking a look at this paper by Leslie Valiant, who was a Turing Award winner actually for his work in parallel computing. And I think this is a very nice algorithm in terms of its conceptual complexity, let's say, or simplicity. Basically, the idea is very simple. You want to the goal is to balance network load. We don't care about latency here. We want to utilize the links as much as possible and balance the load that we have. Then what do you do? In a simple way. Basically, the idea over here is to randomly choose. You don't route from x to y directly. Okay, ignore all the color here. Think about the mesh. We're going to route from 0 to 0 to 63 to 63 over here. And we want to balance the network load. XY routing, okay, simple. Maybe we want to build on XY routing. But we don't want to do that all the time, right? If we want to balance the network load, we want to utilize things as much as possible. And the idea over here is you find a random node in between the destination and the source, and you first route to that random node, intermediate node. So you pick randomly any of the 62 nodes remaining and route the message there first, and then from there to the destination, you can use XY routing. Actually, from each of the pieces, in each of the pieces you can use XY routing. For example, you can go from, let's assume that you pick the random node as this one. You first go this way, and then you go this way. That's the idea. And every time you pick a different random node, that way you hopefully balance the network load. And every single other node also does the same thing, and you balance the network load. And this is oblivious clearly, right? Oblivious in the sense that it's oblivious to the state of the network. There might be congestion, there might be no congestion, then you're still doing it, which may be a bad idea, because you may actually increase your latency, because if you're at this node over here and you want to send a message over here, you randomly pick this node over here to route to first, you increase the latency clearly, right? So clearly in terms of practicality, you need to restrict this a little bit, and we will talk about that restriction. But if you really want, if your goal is the first one over here, this actually achieves the goal. Yeah, that's the idea. So how do you actually make this simpler? It achieves the goal, randomizes and balances the network load. It's non-minimal, actually, because packet latency can increase now. But you can optimize this. Basically, you can do this on potentially high load. Not necessarily a good idea, because if it's too high load, then you may be increasing the load. But you need to keep load under control anyway, I think, or you need to keep the congestion that you're causing because of this load balancing under control anyway. So you can and a good way of doing this is by just restricting the intermediate node. So you basically restrict the intermediate node to be relatively close. That's one example, right? Of course, then the question is, what does close mean? Is it close to the source, or is it close to the destination, right? Or maybe it's both, right? Basically, if you restrict the intermediate node in this quadrant over here, you don't run into the problem of sending this packet all the way to some other random place in the network. Right? You basically restrict your latency bound over here. That's the idea. And I think that's a very good implementation of this approach by dividing the network into quadrants, and you pick your random node from one of the quadrants or from the nearby quadrants. But you don't do it every time. You do it because if your network load balance is not a problem, you just don't need to do this, right? You're basically increasing latency for no reason. You want to do this when you want to actually avoid congestion somehow, but you don't want to keep track of congestion because it's oblivious, remember? If you can keep track of congestion, then you can do something more potentially, right? Which is adaptive, which we will talk about. Okay, so that's the idea. And you can look at a theoretical analysis of this in this paper over here. Okay, and actually there are multiple papers, and I would recommend both of them if you're interested. You can see that these were published in Theory of Computing conferences in 1980s. Okay, and the last one, and probably the most complicated one, is adaptive routing in the end, the routing styles. And we already discussed actually both of them, minimal adaptive and non-minimal, or non-minimal adaptive is sometimes called fully adaptive because you have no restrictions on adaptivity here. In minimal adaptive, router uses network state, for example, the downstream buffer occupancy, to pick which productive output port to send a packet to. Productive meaning it reduces the distance to the destination, as we discussed. Port that gets the packet closer to its destination. Non-minimal basically gets rid of that restriction. This is also called misrouting. In a sense, it's misrouting because your goal in routing is routing the packet to a destination, and misrouting means you're increasing the latency to the destination, right? But you may be temporarily increasing the latency. Eventually, you'll get there, right? That's the idea. This is taking the scenic path, right, as opposed to taking the fastest path. And that's why I like this, because in real world, we do this all the time, right? We don't always take the fastest path because fastest path may be congested or there might be some other problem over there, right? Okay, basically it misroutes packets to a non-productive output port, non-productive output ports, because there could be many non-productive output ports actually, based on network state. So this is minimal adaptive, aware of local congestion, but minimality restricts achievable link utilization, basically load balance in the end. Whereas non-minimality actually enables much better network utilization and load balance. It sometimes can reduce latency also because it reduces the congestion in a very congested part of the network. But now you have another problem. You actually have a live lock freedom problem, right? Meaning, how do you guarantee a packet to reach its destination eventually in the presence of latencies or distance increasing, right? You basically keep sending the packet somewhere else, and the packet may never reach its destination. The packet may always keep circling around, right? That's the beauty of minimal routing algorithms. You don't need to worry about this live lock, because by construction, you made your algorithm minimal. You never choose a non-productive output port. And hopefully, once the congestion reduces, you keep going, right? That's the idea. Here, that doesn't happen. You need to guarantee live lock freedom. In the worst case, you need to guarantee both live lock freedom and deadlock freedom. But usually, there's a trade-off between live lock and deadlock, as we will see in bufferless networks. You get rid of deadlocks, and what you need to solve is live locks then. Okay, you'll understand this more when we talk about bufferless, perhaps. But there are cases where you can have both, actually. Because you need to, bufferless is a special case. You don't have buffers, which means that you've eliminated some resource where you could have a circular dependency on. But if you have both buffers and non-minimal routing, then you actually need to solve both deadlock and live lock problems potentially. But the good thing is, non-minimal routing could be one way of solving the deadlock problem. Okay, so more on adaptive routing. Actually, adaptive routing is necessary, in my opinion, in existing systems, because you really need to avoid faulty links and routers. And with the level at which links and routers are failing, not necessary in the sense that necessary if you want to keep the operation in the presence of faults, right? If you detect the fault, and if you reconfigure the network offline, then you can clearly solve the fault problem with different type of routing algorithms also. But if you want to keep continuous operation in the presence of faults, adaptive routing is really unavoidable, in my opinion. Basically, the idea is route around the faults, clearly. It turns out this is easier said than done. If you want to do it, it causes a lot of issues. And I'll show you a couple of papers that talk about it, but I'm not going to go into detail. Basically, deterministic routing cannot handle faulty components. Oblivious routing is oblivious to it, actually, but you need to be adaptive, basically. But if the downside is now you need to change the routing table to disable faulty nodes, assuming the faulty link and router is detected. So there needs to be some assumption over here. Again, I'm not going to go into this, but it turns out you still need to guarantee deadlock freedom in this case, and you need to fix your tables. And if you have a lot of faults, you may actually now form islands, right? Meaning your network connectivity may go down in the entire network, and you need to discover that also, right? So it's not an easy problem in the end. And there's a lot of work in this area, and this is one of the works that we have done relatively recently, and you can take a look at it if you're interested. It covers different approaches, but as I said, there's a lot of work, especially if you want to do a lot of these things at the same time. In the end, your design choice is not just route around faults. You also want to guarantee delivery, you want to have high performance. Clearly that's not said ever, because it's what you want in general. And you also want to do this not in a globally synchronized manner, right? If you have global synchronization, meaning there's an overseer of the network, a control node that can see everything on the network, then things are relatively easy. But that's a scalability bottleneck in general. You really want distributed algorithms that can take advantage of the distributed nature of the network in general. Okay, I'm not going to bore you with that, but this is an important area for sure. Okay, I think in the last 15 minutes I'm going to cover the buffering and flow control also. Any questions? If you want to stop me, this is a good time. Okay, that means that you don't want to stop me. Okay, recall we talked about circuit versus packet switching, and we said that circuit switching is actually very amenable to buffering or eliminating buffering. But let's talk about what do we need to store in the packet. This is a bit boring, so I'm going to go through this relatively quickly. But clearly in a packet, you need to store the data or control or payload that you need to communicate. You need to have a header that has the routing and control information. What is the destination node, what kind of a packet it is, whatever control information basically. And you have some error code, meaning, or checksum or some CRC basically, that is basically used to correct errors, right? You could also have some security stuff, but we're not going to talk about that. So basically this is what a packet looks like. And there are many ways of handling these packets in general. But let's talk about handling contention first, and I'm going to talk about other things later. This is very fundamental. Although I've given you a bunch of answers, I've given you all of the answers over here. Let's assume that you have these two packets, white ones for whatever reason, and they want to go through this output port. They both want this output port, but clearly they cannot both be scheduled on the same output port in the same cycle. What do you do? What does the router do? One option is clearly buffer one, right? And that's the overwhelming majority of the networks. That's what they do. But what other options do you have? I think I already given you options, so I'm going to go through this relatively quick. You can drop one. But this has different implications. If you buffer one, you need to have buffers. If you drop one, you need to have a mechanism to retransmit. You need to have a mechanism to tell the sender to retransmit. Right? And you also misroute one. You've already seen this actually, misrouting. Basically, this packet, both packets want to go this way. You allow packet A to go that way, and you tell packet A, you go this way, even though that's not the minimal route. And packet A hopefully goes around and comes back. That's the idea. All of these options are actually valid in my opinion, and you need to use them carefully. If you really want to design a good network, I believe you should really use all of these options somehow, because everyone has advantages and disadvantages in the end, as we will see. So clearly there are a lot of trade-offs, and we will see some of these trade-offs hopefully in the next lecture. But misrouting, as I said, requires live lock freedom, and it turns out router complexity is also very different in each of these. For example, if you do buffering, you may need a lot of buffers to ensure that your network is actually working nicely. If you don't use buffering at all, then maybe you're not able to inject a lot of things into your network. So your performance may be inherently lower actually. But your complexity of the routers will be much lower also. That's the upside. So there's an interesting trade-off over here. Dropping is actually interesting because dropping is actually very costly, right? Dropping is much costlier than misrouting. Misrouting, okay, you have some congestion over here, you misroute and you go back here, maybe in the next router. Maybe in the next router it's fixed. Dropping, this router that's far away over here sent its packet all the way here, and then I'm going to drop its packet. You got to be very careful with dropping, I think. Internet drops packets clearly. That's one of the reasons why it's slow. But Internet is also very flexible. It also buffers packets. It also misroutes packets. Internet actually does all of this in the end because it's very flexible. It has the capacity to be that flexible. But some of the networks that are designed in actually real supercomputers are not as flexible. Okay, but this is very important, handling contention, and we're going to get to it. So, and this brings us to actually flow control methods. Basically, what do you do with the packets? You have a packet, and you need to actually route it to its destination. What are the flow control methods that you can use? And we've seen circuit switching clearly. And I'm not going to cover circuit switching more, but then you can do packet switching. But then how do you do the packet switching? Actually, circuit switching can use bufferless also. There's some terminology issue here. So bufferless actually can be both circuit switched and packet and flit based, but packet switch methods are over here. So let's talk about circuits. I guess I will talk about circuit switching very quickly. We've already discussed this. Here the resource allocation granularity is high. It's not a packet based mechanism. As a result, you basically busy the entire circuit for a long amount of time because you pre-allocate the resource across multiple switches for a given flow. So it's not packet based because you're really not allocating on a packet basis, you're allocating on a flow basis. Flow is also referred to as source destination pair, basically, communicating source destination pair. So you need to send a probe to set up the path for pre-allocation. Of course, there are a lot of benefits, no need for buffering, no contention for that flow. And you can handle arbitrary message sizes. This is a different way of thinking about circuit switching than I mentioned before. But as we discussed, you get lower link utilization because two flows cannot use the same link, and you get handshake overhead to set up a circuit. Okay. So circuit switching is actually very good for bufferless, as you can see, because there's inherently no need for buffering. But when you're packet switch, you can also be bufferless. That's the second flow control method. And this is bufferless deflection routing. It's also called hot potato routing. Basically, you can think of routers as humans, and you have a hot potato that you need to send from one human to another human, and it's too hot, you cannot hold it, right? You cannot buffer it, so you basically keep pushing it to someone else. And the hope is that the destination human eventually gets this hot potato, right? And does whatever he or she does with it. That's a very nice name, I think. It's hot potato routing. And it was introduced by this paper, which was originally written in 1962 as a technical report, as you can see, by Paul Brown. That's actually a very seminal paper in the area talking about distributed communication networks. But basically the idea is what I said. You cannot buffer anything in the router. When two packets contend for the same link, one is deflected. Okay, so let's take a look at an example over here. I have a lot of nice pictures on bufferless routing because we've done a lot of work in this area. But basically, you look at this blue packet and this red packet. They both want to go to this destination, and they both reach a router. And unfortunately, only one of them can be transmitted on this output link. So what do? The red one gets prioritized for whatever reason, and the red one reaches destination next cycle, but the blue one traverses around. That's the idea. It takes a scenic route over here. Longer route, but eventually gets there, and the routers are less complex because they don't have buffers. And okay, of course you need to ensure that injection happens correctly. You need to inject new traffic whenever there's a free output link. Again, there's no buffers in the routers. They need to handle injection and ejection carefully here. Okay, but we're going to talk about that later. But this is a way of actually simplifying the network, but this is clearly a way of doing flow control also. We're not going to talk a lot about exactly how you do the buffering in a router, but there are many options here. You can do input buffering, and you could do output buffering. You could do input and output buffering, which I think is not necessary at all. I think input buffering is not necessary at all also. But there are different choices here. You can read papers related to it. But basically, you can eliminate the buffers in bufferless deflection routing. You buffer the packets in pipeline latches or network links. So while the packet is being transmitted, or pieces of a packet is being transmitted, it's buffered on the link. So wires are acting as buffers right now, basically. You don't need any additional buffers. Of course, if you pipeline the wires, and you do need to pipeline things at the beginning of a router, for example, then you actually store things in a pipeline latch. But that's very different from a buffer. Pipeline latch is there to ensure that you operate at some frequency. You keep stuff there. Buffer is there for scheduling, for example, right? Buffer is there to handle the injection. Somebody injects, and you need to keep them in some space. And that buffer is separate from the pipeline latch. Okay, basically you get rid of the pipeline latches, or you get rid of the buffers, and your router is actually simple. Now we're going to see that story is a bit different later, but overall it's conceptually simple, and that's the beauty of this bufferless routing. And if you're interested, basically the issues that result from it are live lock, as we will see later. Router complexity reduces in some way, but also increases in some other way. And we will discuss that. Your critical path increases if you don't handle live lock in a good way. Because live lock is very important. You need to handle live lock, and one way of handling the live lock is ensuring that every packet eventually progresses, right? You need to basically have some bound. But to be able to ensure that every packet eventually progresses to its destination, you somehow need to impose a total order on the packets. And that total order, if it's not imposed in a nice way in the sense that in an implementable way, it could actually increase router complexity significantly, it turns out. And you will see that that problem can be solved. Okay, but the problem that is actually very difficult to solve in bufferless networks in general is performance and congestion at high loads. High load means a lot of sources are injecting, there's a lot of load on the network. If you don't have buffers, fundamentally you're limited in terms of the throughput that you can achieve. And we will see that when we talk more about this. Okay, and this is a paper that is recommended. I don't know if we don't have another homework, so I guess I cannot require it anymore, but I'd recommend reading it. And this is a more low complexity implementation of that bufferless router. And it turns out if you want to achieve high loads, you cannot just go bufferless purely. You actually need some buffers, but you need to use those buffers in a different way. And I recommend looking into these papers. And this summarizes our 6 years of research on this one, but it's not actually comprehensive because we did more research after this also. It's a fun topic. Okay, let me go through some other forms of flow control, and then we'll finish today. Basically, once you decide you do buffering, you need to do something different, basically. Buffering actually causes a lot of headaches, and you actually need to do things nicely. So store and forward flow control is a packet-based flow control method. Basically, how do you deal with the packets in the network when you have buffers? In this case, store and forward, you copy the entire packet into a buffer in the network router before it moves to the next node. Basically, this is your buffer, this is your packet, and flow control unit is the entire packet. So let me see actually. So basically, this is what happens. Before any part of the packet moves to the next router, it needs to be buffered in the router. Makes sense, right? Because you're doing flow control at the packet granularity, and as a result this leads to high per packet latency, and it requires buffering for entire packet in each node. So it turns out this is not very efficient. Okay, this keeps going to the destination. As you can see, it takes a long time. Then the question is, can we do better? And people actually do better. So what they do is, one example is cut-through flow control. I go through this relatively quickly also because it's not the state of the art also. Basically it's another form of packet-based flow control. You start forwarding pieces of the packet as soon as the header is received and the resources are allocated. So you basically leads to a huge reduction in latency, and you can still allocate buffers and channel bandwidth for full packets over here. Basically, look at, you have this buffer over here. You can start forwarding the packet, but you can start forwarding from the next router also into the next router. So basically, now packets are distributed across routers. But you need to manage the buffer allocation very carefully over here. I'm not going to go through this in detail. There's a lot of details here, but I'll spare you with those details. But basically, it's a problem because here you can move the packet. That's good. You reduce the latency, but you still need to allocate buffers for the entire packet because it could be that the entire packet can actually reside in a single node. And if the packets are large, you have an additional overhead. Basically, you have an output port that's blocked. And you can let the tail to continue when the head is blocked, absorbing the whole message into a single switch. Basically, that's what cut-through flow control is. But it requires a large buffer, a buffer that's large enough to hold the largest packet, essentially. So here, as I said earlier, you can let the packet move piece by piece, but you still need to allocate the entire buffer for the packet. Okay. Again, I'm not going to go through the details. There are technical details as to why this is the case. It's a bit boring. But fine, let's move to the state of the art. So this degenerates store and forward with high contention. That's why this doesn't work very well. Then the question is, can we do better? And this is more state of the art basically. It's called wormhole flow control. You basically do flit level flow control in the end. You basically, packets are broken into potentially smaller flits. And flit is the buffer and bandwidth allocation unit. That's how you do the flow control here. Flits are sent across the fabric in a wormhole fashion. So this is the wormhole fashion. This is your head flit. Head flit is in one router. Second flit in the body is in another router. Next flit is another router, and the tail is another router. It's like a worm that's distributed across different routers over here. So body follows head, and rest of the packet stops. And routing information is only in the head, although you could change that as well, as we see in the paper. So how does the body or tail know where to go? Basically, header actually sets up some information in the router saying that I'm this packet, and my body flits will go the same way. Essentially, arbitration is really done by this header packet over here. So it's or header flit over here. I keep using packet and flit sometimes interchangeably, but that's not true. But basically, this is the header flit, which is a portion of the packet itself, and only it participates in the arbitration, and everybody follows as a worm. Okay, in this case, latency is almost independent of distance for long messages, because you basically partition a message or packet into many flits across the entire network. So you could have a huge worm that's partitioned across the entire network, right? That's the idea. Okay. So there are clear advantages over store and forward control. That's lower latency and more efficient buffer utilization. You don't need to have buffers for the entire packet in a single node, but there are also limitations. It suffers from what is known as head of line blocking. If a head flit cannot move due to contention, another worm cannot proceed, even though its links may be idle. This is an example over here. So these are the input queues that you have, and basically 1 means it requires output port 1, 2 means it requires output port 2. These are the input port numbers. And as you can see, both of these queues require output port 1. And what happens is one of them gets it, and the other one cannot get it, but this other output port now becomes not utilized because you're not doing out of order scheduling over here, right? So because you're just looking at these queues over here, and you're just looking at the top element on the queues, or top flit on the queues, or the head flit on the queues, you cannot look beyond and see what packets or what flits are there. And these flits that otherwise need output port 2 don't get scheduled, even though output port 2 is available. Right. This is called head of line blocking. It's the reason this happens is because there is a lack of out of order scheduling in these queues. Right. Now, if you design a high performance microprocessor, you would probably say this sounds stupid, right? Why don't you actually do out of order scheduling over here? In the sense that for each port, you can figure out which packets can actually utilize it, right? And you never leave a port idle. Now it turns out that is true, but the complexity is relatively high if you do out of order scheduling over here. And we know that the complexity is very high if you do out of order scheduling in a high performance processor also, in instruction scheduling. So okay, I think this is a place where I will stop, but this is maybe this is the last line I will stop at. Basically, head of line blocking happens because a worm can be before another in the router input buffer, and due to the FIFO nature, not out of order nature, first in first out nature, the second worm cannot be scheduled, even though it may need to access another output port. Right. Basically, as a result, you have underutilization, and you have longer latency, and you have congestion on the end. So one way of solving this problem is really out of order scheduling, but that increases the complexity of the router. Another way of solving this problem, or alleviating this problem, is what's called virtual channels, which we're going to talk about. Basically, you divide this into virtual channels such that you could actually schedule from some. You don't just look at the head, but you kind of divide this into multiple queues, and that leads to looking at 2 different heads over here potentially. So let's take a look at it over here. Let's assume that this link is blocked by other packets over here, so this green one cannot move. As a result, this purple one cannot move also. So this blue one is making progress. The buffer is full over here. The blue one cannot proceed, right? And as a result, it's blocked. Even though, it's blocked over here. And then the red one comes in. This channel is idle completely, but the red packet is blocked behind the blue one. Blue one needs to go this way, red one needs to go this way, but the red one cannot make progress over here because the blue one is blocking it in the FIFO queue. So you may think that, oh, this is stupid, why don't we have an arbiter that's more complex? And yes, that's right. You need to have an arbiter that's more complex, but if you don't want to increase complexity too much. And then the red holds this channel, the channel remains idle until the red one proceeds over there. So one solution to this is called virtual channel flow control. The idea is very simple. You don't have a single FIFO queue to look at, to arbitrate. You basically have multiple FIFO queues for each input port. That's the idea. It looks like this basically. This is your input port, as opposed to having a single FIFO queue, which is vulnerable to this head of line blocking. You have multiple FIFO queues. Or you can think of it as multiplexing multiple channels over one physical channel. You divide up the input buffer into multiple simple buffers. Now you of course have the question, whenever you get a packet or flit, which queue do you put it in? Now you actually, if you want to minimize head of line blocking, you need to be a little bit more intelligent, but I'm not going to go into the details of that. Now we are making the router more complex, right? And that's the paper that introduced the idea. So you can think of it this way. You have 16 flit FIFO buffers, as opposed to having a single FIFO buffer, you have four flit FIFO buffers. And now you can actually, you do the arbitration on the head of each of the queues. So you have actually 4 things to choose. Here you can choose only one thing. Looks like my battery died here. Here you can choose only the head over here. As a result, you're vulnerable to head of line blocking. I cannot find that. Okay, yeah, you can choose only this. Now you can choose only 4 of those. If you actually had complete out of order scheduling, you could choose any 16, right? But that's expensive. Right? Okay, so basically virtual channel flow control enables you to have 2 smaller queues. If you're blocked by other packets over here, that's okay. Your buffer can become full. Blue cannot proceed over here. But now there's a queue for the red one. And the red one can proceed. It's not blocked anymore. But now we made the router more complicated. A modern virtual channel-based router looks like this. And we're going to stop in a little bit. But basically, you need to manage these input buffers, the virtual channels. You need to decide where to put an input flow. And then you need to do the arbitration. There's routing logic. Essentially, you need to have a virtual channel allocator. You need to have a switch allocator to figure out which virtual channel should be input into this flit, into the switch, and how should the switch be configured. And of course, you need to do the route computation logic. And there's also another thing. You need to actually handle, there's something that's coming in, credits in. This is credit-based flow control. This basically said, can you actually send something to the downstream router? Does the downstream router has enough buffers to handle things? Because that needs to be communicated somehow, and that's not as easy. And that's true for all routers. All routers need to communicate to the upstream routers whether they have buffer availability. Yes?
Why not have the buffers on the output port?
Say it again? Why not have the buffers?
On the output port? Like you have already the crossbar, and you can already disentangle the different...
Yeah, why not have buffers over here, you're asking, right? You could, actually. You could have them in either way. You could have both input and output, or just output, or just input. And there are different trade-offs associated with it. You can think about the trade-offs. Actually, just output buffer routers are not as easy, because you need to handle the arbitration before, right? But you could, no question about that. I'm just showing something without the output buffers over here. Okay, let's see how much do I want to cover this. Okay, let's cover this very quickly. So basically, there are other uses of virtual channels. One is deadlock avoidance. You can enforce switching to a different set of virtual channels on some turns, and that way you can break the cyclic dependency of resources. Actually, if you have a virtual channel, you can steer traffic to another virtual channel. You can enforce order on the virtual channels, and you can have escape virtual channels, have at least one virtual channel that uses deadlock-free routing. Everything else uses deadlock, not non-deadlock-free routing. You can ensure each flit has fair access to that virtual channel. That's another way of handling deadlock, but it's more complicated now, right? You increase the buffering, you increase the virtual channels, and you have multiple routing algorithms in this case. There's also another issue, protocol level deadlock. that can be handled by virtual channels. Protocol level deadlock means essentially you may have different packet classes, requests and replies, and you may have a deadlock because those are preventing each other's delivery. And you can ensure that those different data packets use different virtual channels such that they don't prevent each other. And you can, since we don't have time, I'm not going to go into that much detail. This virtual channels enable prioritization of different traffic classes. Some virtual channels may have higher priority than others. And as a result, you can actually differentiate between different traffic classes. So that's another use of different virtual channels. Okay, so let's review flow control very quickly. Store and forward was like this. You needed to allocate things at the packet granularity, and you need to do the routing at the packet granularity also, which was slow and high buffer overhead. You shrink buffers, reduce latency, you get to cut through and wormhole. I'm going to handle them similarly. And then there are other issues over here, which is head of line blocking. And we solve the head of line blocking by using virtual channels. And I've already animated this. This is head of line blocking. And if you actually use virtual channels, you can get rid of that head of line blocking. But actually, as we went from here to here, we increased the complexity. Even though we improved some of the buffering and reducing latency, we actually made the buffer management more complex. Okay, so there's a lot of complexity involved, and we built essentially almost a state-of-the-art router with the picture that I've shown you. One thing that we didn't discuss is you need to communicate whether a buffer is available or not, right? If you actually want to allocate, if you want to send a packet to a downstream router, you should know whether a buffer is available. If not, then you may have a problem, right? Especially if you have, if you're relying on buffer availability. So these are the different flow control methods that are used to communicate buffer availability upstream. Credit-based, on and off, ACK or NAC. So essentially, credit-based flow control says upstream routers know how many buffers are available downstream. The downstream routers that are receiving the packets pass back credits to the upstream saying, I have this many buffers available. And this leads to a lot of signaling between the routers. So there needs to be another network that carries these credits just to ensure that buffering is done correctly. So it's a lot of overhead, as you can see. We will see an example of this in a little bit. On and off, and also there's delay, right? Of course, you may be sending a lot of packets downstream, but other people may be sending a lot packets to the same router. And the router needs to be conservative because it may actually receive packets from different routers at the same time. So it needs to be conservative in communicating how many buffers it actually has, right? It cannot tell you that it has a lot of buffers and then it runs out of buffers. So there's some delay associated with this credit communication, as well as there are multiple different routers communicating with the same router, so that needs to be taken into account. As a result, your buffering becomes more conservative. You need to over-provision your buffers, or you run out of buffers more quickly. You basically quickly say, oh, I don't have buffers, right? So there's a danger here. That's why a lot of the buffering is over-provisioned in high-performance networks today. So the on and off flow control is a different method. It basically says, stop sending me messages, packets, because I don't have buffers, or now you can start sending me packets. It's on and off, basically. It's different from how many buffers I have credits or not. ACK-NAC is essentially, ACK-NAC means upstream buffer upstream router optimistically sends the packet to downstream router, but it cannot deallocate the buffer until it receives an ACK or NAC. Right. But of course, this may have downsides like inefficient utilization of buffer space. But they all have downsides in the end. Okay, let's take a look at credit-based flow control. You have node 1 and node 2 over here. Let's assume that node 2, at some point, a flit leaves the router. Now we have one buffer available. And at time t1, node 2 sends a credit to node 1. Of course, in this case, it's just node 2 and node 1, right? What if you have node 2 and node 1, node 3, node 4, node 5 that can potentially send to node 2? So you need to send credits to all of them. The question is, how much credit do you need to send? Okay. So if you have only one buffer, you cannot tell everyone that you have one buffer, because now everyone will send you will receive 3 packets in the next cycle. You cannot do that. So you need to over-provision your buffers, or you need to be very conservative when you're sending credits. Either way, either you reduce your energy efficiency because you have a lot of buffering or area cost, or you basically do not utilize your network very well because you tell everyone, I don't have buffers, even though they may not be sending you anything, right? Okay, so you also see that there's a delay associated with this credit round trip. So this node basically will think for some time that it doesn't have a credit. There's also that round trip delay. So it processes that credit and it sends a flit to the next node. And once it sends a flit, it has one buffer available, so it passes the credit back to upstream routers. Again, the same issue exists over here. And then once this node gets the flit, it processes it, and there is a round trip delay associated with even a single flit sending, as you can see over here. Basically, we have a flit, you need to wait for a credit, and then you send the flit, and then only after that it takes some time to fill the buffer, as you can see over here. So from here to here, your buffer is really empty, if you will, for all practical purposes. So you're underutilizing this buffer because of this credit round trip delay. Plus, on top of that, this is just one node and two nodes communicating. So you need to over-provision your buffers. This is why buffering becomes a little bit unwieldy if you want to have high performance. Okay, basically the time between when the buffer empties and when next flit can be processed from that buffer entry, that's credit round trip delay or round trip credit delay. This leads to significant throughput degradation if there are few buffers available. That's why the high performance network over-provision their buffers. And of course, it's important to size the buffers to tolerate this credit turnaround. This is also called turnaround delays. Okay. So let's take a look at another example of this buffering. This is on-off flow control. Again, we have node 1 and node 2. Downstream router node 2 has an on-off signal to upstream to tell the upstream, you can send the buffer, you can send me the flit right now. So node 1 sends a flit. And there, because of that flit received by node 2, the off threshold gets reached, and node 2 tells, okay, I don't have any buffers anymore, so stop sending me. Of course, you need to be careful here. You need to send the signal again conservatively, because if you send it too late, again, a lot of nodes may send you flits and you may not have buffers, right? You need to basically turn off yourself conservatively. And as you can see, that's the conservatism, right? So flits may be still being received over here. So there's some slack that you need to build into this off signal. This off signal assumes that, oh, I'm going to receive some more flits. That's why I'm going to send the off signal even earlier. Okay, so there's some processing delay, and then yeah. Basically, this off threshold is set to prevent flits arriving before T4 from overflowing. Yeah, basically that's not written very well, but basically you need to ensure that the buffers in node 2 do not overflow. So you need to turn off, set that signal at the right time, which means that you need to over-provision your buffers again, right? Or you don't utilize your buffers really well. Okay, and then once node 2 starts sending flits, after some point, you turn on, basically you have enough buffers in this node, and then you can now turn it back on and send an on signal back to any upstream router. Okay, basically it goes on like this. And then now you can keep sending flits, and that processes, and then this can keep receiving flits. Okay, makes sense, right? And this on and off signals are set such that you never overflow these buffers. And as a result, you have conservatism, and your buffers become large. So buffer management is not easy. Basically, that's the whole point over here. And you have a lot of buffers. Especially in complex topologies, this becomes not easy. In a mesh, you really have 4 places where you can receive flits from. Actually, 5 places, right? The input node and northeast, southwest routers. I've just shown you one. You need to actually manage all of these on-off signals for all of them. Okay, I didn't look at ACNAC, but ACNAC actually has similar problems. Okay, so we'll get back to buffering. Let's talk about evaluating interconnection network performance now that we're done with the real basics. Performance is also basics, and I've given you this figure before, right? We talked about load latency curve. This is essentially the load latency curve. Usually if you want to look at an interconnect, you think of it this way. There's some injection rate to the interconnect, and that injection rate can be expressed in different ways. One way of expressing it could be how many flits per node per cycle are being injected, right? And you can have a number based on a workload or based on some particular synthetic pattern, as we've discussed last time, like a uniform random pattern. And that can go from, I guess, 0 to whatever. There's another way of expressing this, basically. It's also called how loaded the system is. It's fraction of the total buffer space and the link space that is utilized. And there's a percentage over here, like maybe 60% of all of the buffer space is utilized. You can also express the load of the network that way, and you may see that in some works. But basically this says how frequently are you injecting into the network. On the y-axis you have the latency. That could be average packet latency or maximum packet latency. Let's talk about average packet latency. And then you have a curve that looks like this usually. Essentially you have some point where you're not injecting anything. You have some latency that's minimal, right? That's called zero load latency. Of course, if you're not injecting anything, how do you measure something? You don't. Basically, this is assuming that some traffic pattern, if the network is not loaded, how long will it take for the packet to go from a source to a destination, right? That's what zero load latency means. And if you keep increasing the load, your latency increases because there's contention. And at some point what happens is network essentially saturates. So this asymptote over here is called saturation throughput. And at that point, your latency shoots up. Sometimes it's called also congestion collapse in the internet, for example. Basically, the network collapses because of congestion. The latencies become too unreasonable at some point. So that's the saturation throughput of the network given a traffic pattern. So this curve is not the same for every traffic pattern, clearly, right? If the traffic pattern is uniform random, meaning any node can communicate with any node in a uniform random manner, that's very different traffic pattern compared to nearest neighbor. Nearest neighbor means a node is communicating only with its left neighbor, let's say, or right neighbor. That is not putting a lot of strain on the network, buffers, links, whatever you have, which means that the curve for nearest neighbor probably looks like this. Right? It saturates very, very late, if it saturates at all. At some point it saturates because you run out of links and buffers, right? But the curve for uniform random looks more closer to here, basically. It saturates much more quickly because every node is sending packets uniformly, randomly to every other node. That's clearly putting a lot more strain on the entire network's resources compared to nearest neighbor traffic. So there are a bunch of different traffic patterns that people analyze usually. Of course, real patterns are somewhere in between probably, right? Okay, so let's take a look at how the fundamentals that we've discussed affect this curve. Because if you think about it, this curve, assuming the traffic pattern, let's pick uniform random. Uniform random is interesting because it basically makes every node equal, and there's no predictable communication pattern in the network. You can think of it as a worst case pattern. It's not really a worst case pattern actually. It just basically is a load balancing pattern. One of the worst case patterns could be a hotspot pattern, right? Hotspot is you have actually, let's say you have a mesh, you have one node that's a hotspot and everybody's sending messages to that node. That saturates the network actually much earlier than uniform random in general. So you see a curve that looks like this very quickly. And if everybody's sending, injecting into the network at a very high rate to that particular hotspot, things get actually congested much, much worse. That's why your routing algorithm is very important, especially with those hotspot patterns. Okay, so let's assume one particular injection pattern, workload pattern. How is this curve, what determines this curve? Basically, there's some minimum latency that's really given by your topology. You cannot go beyond that, right? Your minimum latency, this is actually your diameter, especially your topology's diameter. If your diameter is low, your minimum latency is usually low. If your diameter is high, your minimum latency is high. So topology is very fundamental, as you can see. And on top of that, there is some inefficiency because of your routing algorithm, because you don't necessarily do a good job in routing. Or there's some latency in routing, fundamentally, that affects your minimum latency. So routing algorithm affects that. And on top of that, there's flow control mechanisms, just like we've discussed. All of the buffering overheads, essentially buffering overheads or the management overheads of the flow that adds to your minimum latency. As a result, you get to this point. So topology, routing algorithm, and flow control all together get you to a point over here. Okay, so that's your zero load latency over here. So let's take a look at throughput. Throughput is also, again, bounded by topology over here. Topology bounds your throughput. You cannot go beyond some throughput if your topology is not good enough. And on top of that, you have some inefficiency in your routing because your routing algorithm is not perfect. There's some delay, and it's not high throughput perhaps. And then you lose some throughput because of that. And then on top of that, you lose some throughput because of your flow control mechanisms. And as a result, you reach this asymptote over here. So you're bounded by two asymptotes, the latency asymptote and the throughput asymptote. And they're all affected by, firstly, your topology, and then your routing algorithm, and then your flow control mechanisms. It's good to think about that. Of course, it's hard to exactly figure out what contributes how much to it, and that's part of the design of the network, basically. You want to design a network based on your requirements that minimize these inefficiencies as much as possible. Okay, so I've already said that this is the zero load latency, and that's the saturation throughput. Okay, so basically, a ring topology is very different from a mesh topology, if you think about it. Minimum latency of a ring is much larger for a uniform random traffic pattern compared to a mesh. And we've discussed that. And definitely a point-to-point network is, its minimum latency is much lower, right? Its diameter is 1. And there's no switches that are involved in that transmission. Okay, so ideal latency, we'll go through this very quickly basically, but this is solely due to the wire delay between the source and destination. Usually you want to approximate ideal latency, and point to point is getting very close to that, right? You have only a wire between a source and destination hopefully, but even there's some arbitration delay actually, because you need to figure out which wire to put your message into, right? Because you have many wires connecting yourself to many other routers, many other destinations. But this is the ideal latency. There's some distance. The distance between 2 points measured along axes at right angles, Manhattan distance. And then there's some propagation velocity of the signal. And you have that d divided by v. And also you have some packets, right? You have a packet size and channel bandwidth. And you basically put some number of flits. So that's the ideal latency. And you can study it. It's not that interesting in the end. But on top of ideal latency, you have overheads. Actual latency is you don't have dedicated wires only, but you actually have router latency. So there's additional router latency and the number of hops that you need to travel, plus latency due to contention. And this router latency can be broken down into more, but I'm not going to do that. It's not just the routing latency, but it's also the credit round-trip flow control latency. So there's a lot that goes into the router latency also. And certainly the latency due to contention is not so easy also because it depends on the contention patterns, right? Okay, so this is what a latency and throughput curve looks like. This doesn't have to be on-chip network, but this slide happened to be on-chip network. But basically this is the fraction of the capacity of the network that is occupied, injected, and this is latency, and the curve looks like this usually. And the ideal, you would like this perhaps, right? Maybe this is your really minimum latency. Of course, you could argue that ideal should be much closer to here, but ideally you shouldn't saturate, right? But you do saturate because your network is not ideal. Okay. Any questions so far? Okay, let's look at some network performance metrics. We've talked about packet latency. Round-trip latency could be another one. And packet latency could be average and maximum. Round-trip latency is not just packet latency, but request-response latency. You send a request and you get a response. What is the round-trip delay for that? And saturation throughput we also talked about. So these are actually very traditional performance metrics that people use, and you can actually gather them from here. But I think actually a lot of works, especially in on-chip networks, more recently I focused on application level performance, system performance, and this is really important, as you know by now. This is affected by interference among threads and applications also. So this is really important to consider. So we'll take a more application level view. And if you actually think about the applications, maybe there's a different way of designing networks. In the past, people actually thought about traffic patterns and looked at traffic patterns and the network's performance based on those traffic patterns. That's good, interesting, but you don't know whether those traffic patterns are actually going to be the real patterns that are going to be used in your network. if you look at an on-chip network, actually there are real workloads that are running on that network, and you can actually design your network to the requirements of those workloads.